Hello there, and welcome to Science for Sleep. Where the night becomes gentle, the stars become soft. And the universe opens just wide enough to let your thoughts drift a little farther. A little quieter. A little calmer. Tonight, we're sinking into one of the most subtle mysteries ever hidden in the sky. A slow, steady gravitational pull so vast and so silent that it guides the motion of entire galaxy clusters, including our own Milky Way. Astronomers call it the Great Attractor. But don't worry. There's nothing dramatic waiting for us. Just a peaceful, patient force, woven into the structure of the cosmos. Before we begin, take a moment to settle into whatever space is holding you right now. Let your shoulders soften. Let your breath fall into a slower rhythm. Let the day release its hold on you, bit by bit. This journey isn't one you need to follow closely. No need to remember anything. Just let the words flow around you, the way galaxies flow along their quiet cosmic paths. Imagine yourself floating far beyond the Milky Way, where the galaxy looks like a soft spiral of light. From out here, everything drifts. Everything moves with a kind of ancient purpose. Even our home galaxy is sliding gently through space, carried by a current you can't see. A quiet river of gravity flowing across the universe. As you float in this calm darkness, you begin to feel that pull too. Subtle, steady, peaceful. Nothing urgent. Nothing to fear. Just the universe guiding you toward a deeper stillness. And tonight, we'll explore this hidden current. How we discovered it. What lies behind the thick curtain of our own galaxy. Why so many thousands of galaxies drift in the same direction. And how dark matter shapes invisible landscapes that stretch farther than our minds can truly grasp. These aren't facts to memorize. They're gentle ripples of understanding, meant to soothe your curiosity, instead of demanding your attention. So, whenever you're ready, let's drift together into 101 Sleepy Facts about the Great Attractor. A quiet journey across cosmic tides, guided by gravity older than stars, carrying you softly toward rest. The universe does not expand evenly. When people first learn about the expansion of the universe, they often imagine something simple, galaxies drifting away from one another like dots drawn on a balloon as it inflates. Smooth, symmetrical, predictable. But the real universe is nothing like that perfect balloon. It is uneven, patchy, textured. A cosmic landscape shaped by hidden valleys and subtle slopes of gravity. And because of this unevenness, something remarkable happens. Galaxies don't just expand outward, they drift. Slowly, quietly, persistently. The expansion of the universe is real, but it is not the only motion woven into the fabric of spacetime. Overlaid on top of that expansion is a more delicate movement, an ancient drift caused by the distribution of matter across the cosmic web. Regions with higher mass cause spacetime to curve more deeply, creating gentle gravitational basins and slopes. Regions with less mass cause weaker curvature, allowing galaxies to drift more freely. And the result is a universe filled with slow, steady currents, cosmic streams that guide entire galaxy clusters without ever announcing their presence. If you were floating far above the universe, looking down on billions of galaxies like soft light scattered across the darkness, you would see it, a delicate flow, like the slow movement of water in a vast and silent sea. The galaxies are not wandering aimlessly. They're gliding, pulled ever so gently along by the contours of gravity sculpted across hundreds of millions of light-years. This fact, simple yet profound, is the beginning of the mystery of the Great Attractor. It is the first whisper that the universe holds hidden forces, silent currents, and invisible patterns that shape everything, from the tiniest dwarf galaxy to the Milky Way itself. Galaxies move with the winds of gravity. If you imagine a galaxy drifting through the void, it's easy to picture it as weightless and independent, free to float wherever it pleases. But the cosmos is not a place of freedom, it is a place of influence. Gravity threads through everything, even the vastest emptiness. Its pull stretches across unimaginable distances. And so galaxies do not simply wander, they follow. Astronomers sometimes describe the movement of galaxies as being carried by gravitational winds. Not winds made of air or particles, but invisible flows of spacetime curvature. These winds are soft but persistent. They do not push suddenly or violently. Instead, they guide gently, like a slow tide that even the strongest swimmer cannot escape. A galaxy may spin beautifully, lights swirling with the grace of stars, but beneath that spin is a deeper motion, a long drift shaped by the distribution of matter in regions far beyond its own spiral arms. These gravitational winds form when matter gathers unevenly across the universe. A cluster over here, a filament over there, a void stretching behind them. Gravity flows from empty regions toward dense ones, carving pathways through the cosmic web. Over billions of years, galaxies align themselves with these invisible paths, drifting along them like leaves moving with a slow current. And though you cannot feel this movement with your senses, and though no telescope shows it unfolding in real time, the galaxies obey it faithfully. It is this obedience to gravity's subtle design that reveals the deeper landscape of the universe, one where the hidden, not the visible, dictates the path forward. The Milky Way is sliding through space at hundreds of kilometers per second. Our home galaxy feels still, anchored, familiar. But this is an illusion created by scale. In truth, the Milky Way is moving, swiftly, silently, and endlessly, through space. Relative to the cosmic microwave background, our galaxy is drifting at a speed of around 600 kilometers per second. That's fast enough to cross the distance from Earth to the Moon in less than a second. And yet, despite this tremendous speed, the motion feels slow. Cosmic distances are so vast that even hundreds of kilometers per second translate into glacial progress. If you were watching from far above the universe, you would not see the Milky Way racing, you would see it drifting, like a small boat gliding across a dark, endless ocean. This movement did not begin with the Milky Way's birth. It started long before, when the dark matter halo that would one day cradle our galaxy formed and began sliding along the gravitational contours of the young universe. As stars ignited, as spiral arms unfurled, as planets coalesced, the drift continued, unchanged, unhurried, ancient. Even now, every star we see in the night sky moves with this incredible velocity, though the movement is far too slow for any human lifetime to detect without precise instruments. This cosmic drift reminds us that our galaxy is not a fixed landmark. In space, it is a traveler. A quiet voyager pulled along a path shaped by forces far larger and older than itself. This motion cannot be explained by expansion alone. If cosmic expansion were the only force at work, the Milky Way's motion would be simple and predictable. It would drift outward, away from other galaxies, just as Hubble's law describes. But the actual motion of the Milky Way, and of many galaxies around us, shows something more complicated. Our galaxy is not just moving away from others. It is also moving sideways, slipping through space toward a specific direction in the sky. This sideways motion is the part that cannot be explained by cosmic expansion. Expansion spreads galaxies apart uniformly. It cannot generate coordinated sideways drift. It cannot make clusters lean, tilt, or slide in the same direction. Something else must be at work, something more subtle, hidden, and immense. For decades, astronomers tried to understand this strange movement. Why were galaxies sliding sideways? Why was the Milky Way moving toward a region where nothing obvious could be seen? Expansion alone could not account for this. Local clusters did not have enough mass to cause such motion. Even the Virgo cluster, our nearest major neighbor, was not sufficient. This mismatch between prediction and observation became one of the cosmic puzzles of the late 20th century. Something was pulling on us, something with tremendous gravitational influence, but it was not visible. It was not bright. It was not obvious. And because it lay behind the dense plane of the Milky Way, it was hidden behind a curtain of dust and stars. This sideways drift became one of the strongest hints that the universe contains gravitational structures we cannot easily see, and that the Great Attractor was not just a metaphor, but a real region quietly shaping the motion of galaxies across a vast domain of space. The drift reveals a deeper, more silent gravitational force. When astronomers realized the Milky Way was not moving randomly but being pulled, they began searching for the source. At first, the search seemed simple: look for a massive cluster. But what they found, or rather, what they didn't find, made the mystery even deeper. They expected to see a bright beacon of galaxies. A brilliant cluster shining through space. But the region we were drifting toward appeared dim, quiet, almost empty. This silence suggested something profound. The gravitational influence pulling us is not fully visible. Gravity does not care whether matter shines. It does not distinguish between glowing stars and cold dark matter. It pulls on everything equally. So a structure rich in dark matter could have enormous gravitational influence without giving off much light. And that is exactly what the drift suggested: a deep, quiet well of gravity shaped by matter we could not see, matter that existed behind the Milky Way's thick screen of dust. Or matter that emitted no light at all. This hidden force became known as the Great Attractor. But even that name does not capture the true nature of the region. The Great Attractor is not a single object. It is an extended gravitational basin, a landscape carved by the mass of clusters, filaments, and dark matter halos layered on top of one another. It is not bright, but it is powerful. And it is powerful not loudly, not forcefully, but quietly, in the way a deep valley quietly shapes the path of a river without ever being seen. The drift of our galaxy, the silent motion through the cosmic night, is the handwriting of this force. A message written not in light, but in motion. A message that the universe speaks softly, yet unmistakably. Neighboring galaxies drift in the same direction. When astronomers mapped the motions of galaxies around us, they noticed something remarkable: the Milky Way is not drifting alone. Our neighboring galaxies, the Andromeda Galaxy, the Triangulum Galaxy, the Sculptor Group, the Centaurus groups, and many more, are all gliding in nearly the same direction, as though caught in a shared current. This isn't coincidence. Galaxies separated by tens of millions of light-years shouldn't share the same sideways drift unless something enormous, a gravitational field much larger than any one cluster, pulls on them all at once. Imagine standing on the shore and watching small boats scattered across a wide bay. They are far apart, each built differently, each pointed in its own direction. Yet, despite their differences, you begin to notice they're all drifting the same way. There's no wind you can feel, no tide you can see. But the boats agree with one another, silently revealing the presence of a deeper current. That is what astronomers saw. Dozens, then hundreds, then thousands of galaxies, all leaning subtly toward the same dusty patch of sky hidden behind the Milky Way. This pattern of agreement is one of the clearest signatures of a large-scale gravitational influence. Galaxies respond to the shape of spacetime, and if many galaxies follow the same slope, that slope must be vast, far larger than any one cluster or filament. Our galaxy, this great swirling disk of 400 billion stars, is only one passenger in a long convoy of cosmic travelers drifting toward a hidden gravitational valley. And like leaves carried by a tide, these galaxies reveal the path even when the source of the pull remains unseen. This sideways motion is called peculiar velocity. In astronomy, the word peculiar doesn't mean strange. It means additional, an extra motion layered on top of the universal expansion of space. All galaxies participate in the Hubble expansion, but peculiar velocity is that extra bit of movement that doesn't match the simple, moving apart, pattern. Peculiar velocity is incredibly subtle. You can't see it in one lifetime. You can't watch a galaxy shift across the sky in real time. It is measured only through the light the galaxy emits, how that light is stretched or compressed. Yet this faint whisper in the wavelength of starlight carries immense information. In a universe with perfectly even expansion and perfectly even matter distribution, peculiar velocities would be nearly zero. Galaxies would drift apart smoothly with little sideways motion. But our universe is not smooth. It has texture, peaks and valleys of mass, clusters and voids, filaments and gravitational basins. Peculiar velocity is the gentle response of galaxies to this uneven landscape. It is the sideways tug of gravity. The quiet lean of a galaxy toward a deeper region. The soft signature of invisible structures. Peculiar velocity is how the universe speaks when light cannot pass, when dust obscures, when structures hide behind the Milky Way's glowing band. Even when a region is hidden, its gravity leaves fingerprints in the peculiar velocities of nearby galaxies. And so peculiar velocity becomes one of the most valuable clues in cosmic cartography, an invisible pen tracing the curves of the gravitational terrain. Peculiar velocity is not strange at all, it's natural. To human intuition, the idea that galaxies drift sideways seems odd. In everyday life, objects move with direct causes, winds, engines, impacts. But on cosmic scales, motion emerges from something much quieter, the shape of spacetime itself. Once you imagine the universe as a gravitational landscape, peculiar velocity becomes not strange, but inevitable. Matter naturally moves toward regions of higher density, just as water flows downhill. Even the tiniest imbalance in matter distribution produces subtle gravitational gradients. Over billions of years, those gradients guide galaxies along slow, sweeping paths. In fact, if peculiar velocities did not exist, that would be the strange scenario. It would mean the universe was unnaturally uniform, perfectly symmetrical, without filaments, without voids, without the cosmic web we observe today. Peculiar velocity is simply the motion of galaxies responding to the large-scale structure that gravity has carved into the universe since it was young. Think of it like this. Filaments of dark matter form cosmic rivers. Clusters form gravitational lakes. Superclusters form vast, sprawling basins. Peculiar velocity is the gentle current created by all of the above. It is the natural flow of matter toward deeper gravitational potentials. So the sideways drift of the Milky Way, and of its neighboring galaxies, is not an anomaly. It is a sign that the universe is working exactly as gravity intends. Peculiar velocity reveals regions of high density. Light tells us what shines. Gravity tells us what exists. Even when a region is obscured by dust or too faint to detect, its gravity pulls on the galaxies around it. Peculiar velocity is the observable effect of that pull. In this way, peculiar velocity becomes a detective's tool, unveiling hidden concentrations of matter that light cannot reveal. If galaxies are drifting toward a region, that region must contain mass, possibly enormous amounts of mass. The greater the peculiar velocity, the deeper the gravitational well. Astronomers use this principle to map the unseen structure of the universe. This method revealed several major truths. Regions behind the Milky Way's dust band are not empty, they contain clusters. Some of those clusters are massive enough to influence the motion of entire superclusters. The Great Attractor cannot be explained without invoking hidden mass and dark matter. Peculiar velocity is how we first learned the universe has currents. It is how we discovered gravitational basins. It is how we first sensed the presence of the Great Attractor long before we could image anything in that direction. In essence, peculiar velocity is the universe whispering where the mass is, whether or not the light is visible. The Milky Way is not stationary, it is sliding through the dark. It's easy to imagine the Milky Way as a fixed point in space. Stable. Steady. Anchored. After all, the stars appear unmoving to our eyes. The constellations persist across centuries. But this perception is only a reflection of our tiny timescale. On cosmic timescales, nothing is stationary. The Milky Way is sweeping through the universe with incredible speed. Not because something is pushing it, but because gravity is guiding it. Everything inside the galaxy, every star, every planet, every drifting cloud of nebulous dust, moves together as a coherent whole, sliding along the gravitational contours of the universe. Even the dark matter halo enveloping the Milky Way moves with this drift. If you could zoom out far enough, you would see the entire galaxy traveling like a single glowing leaf carried by a vast, silent river. Our night sky, peaceful and unchanging to us, is actually moving on a scale too large for our senses to perceive. The Milky Way travels through the cosmic web the way a bead rolls through a shallow groove, guided, but not forced. Free, but not aimless. The darkness is not empty around it. The darkness has shape. And we are moving through that shape right now. Many galaxies moving together form a bulk flow. One galaxy drifting sideways is interesting. Dozens drifting in the same direction is curious. Thousands drifting coherently is something else entirely. This coordinated drift is known as bulk flow. And it is one of the most powerful indicators of large-scale gravitational structure. When galaxies across a huge region of space, tens or even hundreds of millions of light-years, move in similar directions, it means they are responding to the same gravitational environment. Bulk flow is like the tide of the universe. It is not violent, not chaotic, not sudden. It is steady and gentle, slow. Enough to be invisible over human history but strong enough to redirect clusters. Bulk flow is what first hinted that the Great Attractor was not a local curiosity but part of an enormous gravitational basin affecting galaxies across a vast region. When astronomers measured galaxy velocities in multiple directions, they found that our entire corner of the universe is drifting toward a single region, almost as if falling into a shallow, invisible valley. This is not random movement. It is structure asserting its influence across enormous scales. And it is one of the quietest, most elegant signatures of the universe's underlying architecture. Coordinated motion reveals a hidden destination. If galaxies were drifting in random directions, there would be no mystery. But they are not. When astronomers traced the direction of the bulk flow, all paths pointed to a specific region in the sky, near the constellations Hydra and Centaurus. And yet, nothing obvious was there. No massive bright cluster. No luminous beacon. Just a crowded, dust-filled part of the Milky Way's disk blocking the view. This was the first sign that the destination of the cosmic drift was hidden, concealed behind the thick interstellar veil we now call the Zone of Avoidance. Thousands of galaxies leaning toward the same unseen region told astronomers. There is mass there. A lot of mass. Far more than what images initially revealed. This discovery transformed the bulk flow from an anomaly into a message. It meant something huge existed behind the Milky Way's midplane, something capable of guiding the motion of entire superclusters. Galaxies do not invent motion. They respond to gravity. And their collective drift drew a straight line toward the heart of the hidden Great Attractor. The destination is not the center of the universe. When people hear Great Attractor, they imagine a central point, a cosmic hub pulling everything inward. But the Great Attractor is not the center of the universe. There is no center. The universe expands everywhere equally. No part is privileged. No location is the origin. Instead, the Great Attractor is simply a region of higher mass density. A gravitational low point. A valley in the fabric of spacetime. It acts the way a depression in a landscape would guide water, not because it is the deepest place in the world, but because it is deeper than the surroundings. Galaxies flow toward it not because it is the ultimate destination, but because it lies downhill from them on the gravitational slope. The beauty of this interpretation is that it restores simplicity. There is no cosmic conspiracy. No secret central point. Only gravity doing what gravity does, creating structure from uneven distributions of matter. Understanding the Great Attractor as a gravitational basin rather than a center allows astronomers to see the universe as a giant web of connections rather than a system orbiting a single point. The Great Attractor is not the heart of the cosmos. It is one of many quiet lows in a vast, uneven gravitational landscape. The drift appears clearly in the cosmic microwave background. The cosmic microwave background, CMB, is the oldest light in the universe, a faint afterglow from 380,000 years after the Big Bang. It fills all of space with almost identical temperature. But almost is the key word. There is a tiny temperature difference across the sky, the CMB dipole. One side of the sky appears slightly warmer. The opposite side appears slightly cooler. This temperature difference is not a real difference in the early universe, it is caused by our motion through space. Just as a car driving into the wind feels a slightly higher pressure on its front side, the Milky Way moving through the CMB sees a slight blue shift in the direction of travel. The opposite direction appears slightly redshifted. This is the CMB dipole. It is the universe's own way of telling us, you are moving. The CMB dipole shows that the Milky Way is drifting toward the same region the bulk flow indicates. Completely independent methods. Completely consistent results. When two separate cosmic measurements point to the same destination, the message is unmistakable. A powerful gravitational influence lies ahead. The CMB shows our motion clearly and unmistakably. The CMB dipole is one of the cleanest measurements in cosmology. Its signal is strong, simple, and robust. The data reveal that our entire galaxy is moving at roughly 600 km per second toward a specific region of the sky. This motion is not due to the rotation of the Earth. Not due to the orbit around the Sun. Not due to the Sun's motion through the Milky Way. All of those effects are carefully subtracted. What remains is our true motion relative to the universe itself. The CMB dipole aligns almost perfectly with the direction indicated by peculiar velocities. This alignment is extraordinary. It means two entirely different measurements, light from the early universe and motion of galaxies today, speak the same truth. The universe is pulling us. Gently. Persistently. Unignorably. And we are moving in response to that pull. This motion is the signature of a massive hidden structure, the Great Attractor. The combined evidence from peculiar velocities, bulk flow, and the CMB dipole all point to the same conclusion: a massive gravitational region is influencing the motion of our galaxy and many others. This region is what astronomers call the Great Attractor. But the Great Attractor is not bright. It does not shine dramatically like a starburst galaxy or a quasar. It is not identifiable at first glance. Its mass is spread across clusters, filaments, and dark matter halos. Much of it lies behind thick clouds of dust. Its defining characteristic is not luminosity, it is influence. The Great Attractor is known not because we see it, but because we feel it, through the movement of galaxies across vast stretches of space. Its signature is motion, not light. Its identity is gravity, not brightness. This shift, from searching for what shines to searching for what pulls, is one of the greatest transformations in modern astronomy. The Great Attractor does not shine brighter than its surroundings. If you were expecting the Great Attractor to look like a glowing cosmic jewel, the reality is far quieter. It shines, normally. Even modestly. Its visible galaxies are not extraordinary in luminosity. The region does not outshine the rest of the sky. This is part of what made it so difficult to identify. Because the Great Attractor is not a single object but a broad region, its brightness is spread out. There is no central beacon. No blinding cluster. No obvious signpost. Instead, the gravitational mass is distributed across multiple structures, including the Norma cluster, the Centaurus cluster, and surrounding filaments, many of which are hidden behind the Milky Way's dust. Brightness is not the language of gravity. Gravity speaks through motion, and motion alone revealed the presence of the Great Attractor. Long before any light from the region could reach us. This is why astronomy is as much a study of absence as of presence. of what cannot be seen, but must be believed because the universe moves. Accordingly, the Great Attractor hides behind the Milky Way's zone of avoidance. The zone of avoidance is a crowded, dusty section of the sky where the Milky Way's dense disk blocks our view of the universe beyond. Optical light cannot pass easily through it. Even the brightest clusters become dim, scattered, or invisible when viewed through this thick band of interstellar material. Unfortunately, or perhaps poetically, the Great Attractor lies directly behind this zone. For decades, this made it nearly impossible to map. Astronomers could measure the peculiar velocities pointing toward the region but could not see what was actually there. It was like trying to find a mountain hidden behind a dense fog. You know the slope exists because water flows downward, but your eyes see nothing but mist. Only when infrared, radio, and X-ray observations advanced did the structures behind the zone of avoidance begin to emerge. The fog parted. Norma cluster appeared. Filaments took shape. The true complexity of the gravitational basin became visible. But even now, the region remains partly obscured, perfect for a cosmic mystery. We sense the Great Attractor through motion, not through light. Most astronomical discoveries are made through light. Telescopes capture photons and translate them into images, spectra, and data. But the Great Attractor breaks this rule. We did not discover it through images. We discovered it through motion. It is gravity's shadow. Not a shadow that blocks light, but one that bends trajectories. The Great Attractor revealed itself by the way galaxies leaned toward it, by the way the CMB dipole tilted in its direction, by the way peculiar velocities across the sky pointed toward the same hidden region. It is an object, not defined by appearance, but by influence. This makes it one of the most quietly powerful structures in the local universe, a gravitational giant whose face is obscured, whose voice is indirect, and whose presence is known only because the cosmos cannot help but drift toward it. The universe begins to look like an ocean with deep, quiet currents. When all of these observations are combined, bulk flow, peculiar velocities, CMB dipole, hidden clusters, you begin to see the universe differently. Not as a static grid of galaxies. Not as a random scattering of points. But as a vast, dark ocean with deep, slow currents guiding everything. The Great Attractor becomes a kind of underwater trench. The galaxies become drifting lanterns carried by ancient tides. The cosmic web becomes a network of currents and channels. The universe is not chaotic, it is patterned. Not violent, it is rhythmic. Not silent, but whispering through motion. Gently, persistently. And you, lying here listening, are drifting through that cosmic ocean with the Milky Way. Carried along a silent pathway millions of light years wide. Toward mysteries hidden behind dust and time. Guided by gravity so soft that you feel none of it. And yet so vast that it shapes the destiny of galaxies. The Great Attractor is not a single object, but a gravitational region. In astronomy, names can sometimes mislead. The Great Attractor sounds like a single, colossal object, something compact and powerful, like a supermassive black hole or an unimaginably bright cluster. But the truth is gentler, broader, and more mysterious. The Great Attractor is not a point. It is a region, a wide gravitational basin created by the combined mass of clusters, filaments, and vast amounts of dark matter stretched across tens of millions of light-years. Its influence is not sharp or sudden. Instead, it's like the slope of a valley, so broad and subtle that galaxies drift across it without ever realizing there is no single peak. This region does not pull like a magnet or swallow like a black hole. Rather, it gently guides the motion of entire galaxy groups, shaping their trajectories over billions of years. The Great Attractor is a reminder that gravity does not require a single source. Sometimes, the deepest influence in the universe comes from the collective weight of many structures, layered softly atop one another, forming a gravitational shape that cannot be pointed to, only sensed through motion. It influences thousands of galaxies across hundreds of millions of light-years. The scale of the Great Attractor's influence is astonishing. Our own Milky Way is just one traveler among many. Thousands of galaxies, some larger, some smaller. Some forming elegant spirals, others rugged ellipticals, are all drifting toward the same region. Their paths may differ slightly, but their overall direction remains consistent, as if an invisible tide is guiding them. This influence stretches across hundreds of millions of light-years, covering vast structures like the Virgo Supercluster, the Hydra-Centaurus region, and even parts of the Pavo-Indus filament. It demonstrates a profound truth about gravity. When you gather enough mass across a large volume, the result is not a sharp pull but a grand, gentle flow. Galaxies respond to this large-scale curvature of spacetime as though drifting down a slow slope carved by ancient mass. The Great Attractor is not king of the universe, it is simply one of the deepest basins in our cosmic neighborhood, shaping the quiet journey of galaxies across enormous distances. It does not shine brightly like the Virgo cluster. When astronomers first suspected a massive gravitational influence in the Hydra-Centaurus region, they expected something bright, something like the Virgo cluster, filled with glowing galaxies and blazing X-ray gas. But the Great Attractor did not cooperate with these expectations. It did not shine fiercely or announce itself with obvious luminosity. Instead, it remained faint, subdued, almost underwhelming. This unexpected faintness is part of what made the mystery so compelling. How could a region powerful enough to affect thousands of galaxies be so dim? The answer turned out to be simple and profound: gravity does not care whether matter glows. Most of the Great Attractor's mass is not in bright stars or radiating gas. Much of it is tied up in dark matter, in hidden clusters, in structures obscured by cosmic dust. The region's gravitational power is immense, yet its light is modest, a quiet giant rather than a blazing beacon. It sits directly behind the Milky Way's thick galactic disk. If the Great Attractor had been located anywhere else in the sky, it might have been identified much earlier. But it lies in an unfortunate direction, straight behind the thick, dusty plain of our own Milky Way. This region, dense with stars, gas, and cosmic dust, forms a natural curtain that blocks our view of whatever lies beyond. As a result, early astronomers had very little visual information to work with. Telescopes could not pierce the dust. Even powerful photographic plates registered only faint hints of light. The region looked empty, yet the gravitational evidence insisted it was anything but empty. This paradox deepened the mystery: how could a place we couldn't see dictate the motion of the entire local group? The answer remained hidden behind the Milky Way's bright midplane, waiting for infrared, radio, and X-ray telescopes to peel back the layers of dust and reveal what optical eyes could not. Dust and dense star fields hide the region from sight. The obscuration caused by the Milky Way's disk is not a simple matter of dimming. The zone of avoidance, the region where the Great Attractor lies, is thick with interstellar dust grains and densely packed star fields. Dust absorbs and scatters visible light, turning bright galaxies into faint smudges or erasing them entirely. Meanwhile, dense star fields overwhelm the background with layers of starlight, making it extremely difficult to distinguish distant galaxies from local ones. Imagine trying to see distant mountains through a blizzard and a glowing city skyline at the same time. The background structures might be vast and magnificent, but their light never reaches your eyes. That is the challenge faced by astronomers studying the Great Attractor in visible wavelengths. It is not an absence of galaxies, only an absence of visibility. The region is rich and complex, but its light must struggle through the Milky Way's dusty veil. We see the effect, not the cause. When astronomers first mapped galaxy velocities and noticed the coherent drift toward the Hydra-Centaurus region, they were perplexed. There was no bright cluster, no colossal object, no obvious cause for such a massive gravitational influence. The effect was undeniable, thousands of galaxies drifting, but the cause remained invisible. This mismatch between motion and observation was one of the most tantalizing puzzles in modern astronomy. It forced scientists to rely on indirect clues, peculiar velocities, redshift surveys, and cosmic microwave background measurements, to infer what lay hidden. Over time, the gravitational portrait became clearer even though the visual picture remained faint. In a way, the Great Attractor taught astronomers an important lesson: the universe does not always reveal itself through light. Sometimes, motion is the only language available. And sometimes, that language is enough to uncover entire hidden worlds. Nearby galaxies all lean toward the same hidden region. One of the strongest indicators that the Great Attractor was real, not an illusion, not an observational mistake, was the consistent motion of nearby galaxies. Independent galaxy groups, separated by tens of millions of light-years, all showed a similar lean in their movement. This subtle leaning cannot be explained by chance. Galaxies, born in different environments and shaped by different histories, should not naturally drift in the same direction unless guided by a shared gravitational field. The fact that they do lean together is a clear sign of a large-scale basin shaping their motion. This coordinated drift formed the backbone of the discovery. It was like watching hundreds of floating lanterns drifting toward the same point in a dark lake, not because of wind or coincidence, but because the lake had a gentle slope in that direction. The region must contain enormous mass. From the magnitude of galaxy velocities alone, astronomers inferred that the hidden region must contain truly extraordinary mass, far more than anything visible through the dust suggested. The gravitational pull required to redirect entire superclusters is immense. Even conservative estimates suggest the mass in the Great Attractor region is equivalent to hundreds of thousands of Milky Way-sized galaxies. Much of this mass is dark matter that neither glows nor absorbs light, but whose gravity shapes the structure of the universe. This concentrated mass forms a gravitational dimple in spacetime so broad that galaxies across the Virgo supercluster feel its presence. The Great Attractor may not be bright, but it is undeniably heavy enough to pull on the trajectories of galaxies millions of light-years away. Early measurements were too shallow to see its true form. In the early decades of studying the Great Attractor, astronomers were limited by technology. Optical surveys could not penetrate the dust. Redshift measurements were sparse. X-ray detectors were weak by today's standards. The first generation of surveys painted only a partial picture, a faint suggestion of a structure, not its full form. It's as if the early observers were sketching a mountain range by looking at its reflection in rippling water. The outline was distorted, the heights unclear, the details invisible. Only later, with deeper infrared surveys, such as 2MASS and Dennis, radio observations, and more sensitive X-ray telescopes, did the true structures in the Hydra-Centaurus region begin to emerge. The more deeply astronomers looked, the more mass they found. Slowly, the Great Attractor transformed from an enigma into a gravitational landscape, the beginning of something larger. It was once mistaken for a single supercluster. When the Great Attractor was first hypothesized, many astronomers assumed it must be a single, massive supercluster, something like a supersized version of Virgo. It seemed logical, if galaxies were drifting toward a region, perhaps a single giant cluster lay there. But as better surveys revealed more detail, the idea of a single cluster faded. Instead, the region turned out to be a complex assembly of multiple clusters, including the Hydra cluster, the Centaurus cluster, and the Norma cluster, all connected by filaments of dark matter. This web-like structure is far more typical of the cosmic web. Gravity rarely forms singular, isolated giants. Instead, it forms interlinked networks. The Great Attractor is not one mountain, it is a mountain range. The reality is far more complex than a single structure. Astronomers eventually realized that the Great Attractor is only the first layer of a much deeper gravitational story. It includes multiple clusters, extended filaments, and higher density regions beyond the zone of avoidance. Even the Hydra-Centaurus supercluster is merely a component of this greater basin. Furthermore, the Great Attractor is not the final destination of the cosmic flow. The gravitational slope continues downward into an even stronger concentration of mass, the Shapley Supercluster, located farther away. So the Great Attractor is not the deepest point in the landscape. It is a stepping stone, a midpoint, a gateway leading toward much larger structures. This realization changed everything about how astronomers view cosmic motion. It is not a giant black hole. Because the name, Great Attractor, evokes something mysterious and powerful, some people wonder whether it might be a gigantic black hole. But that idea does not match the observations. A black hole massive enough to affect entire superclusters would produce intense radiation as matter fell into it. It would distort the motion of galaxies violently, not gently. It would also require unrealistic densities incompatible with large-scale structure. Instead, the Great Attractor behaves like a broad region of mass, not a compact object. Galaxies are not spiraling inward rapidly. They are drifting, slowly, steadily, peacefully. This slow motion is entirely consistent with a cosmic basin, not a deep pit. Gravity on cosmic scales is soft and spacious. Even enormous influences stretch across tens of millions of light-years, producing slopes, not abysses. It does not pull everything in, it simply creates a gravitational slope. Gravity on the largest scales acts more like terrain than like suction. Regions with more mass sit lower in the gravitational landscape. Regions with less mass sit higher. Galaxies flow downhill, toward deeper zones, but they do not fall like stones, they drift like water. The Great Attractor is one such gravitational low point. It does not yank galaxies violently. Instead, it creates a subtle tilt in spacetime, guiding motion over billions of years. The slope is so gentle that the motion is invisible on human timescales. But across cosmic history, the effect accumulates into vast flows. This perspective transforms the Great Attractor from a mysterious monster into a natural feature, one of many contours shaping the cosmic web. We are sliding down that slope with thousands of other galaxies. The Milky Way is not alone in following this gravitational pathway. Entire galaxy groups and superclusters are drifting along the same slope, all gliding toward the same broad region. This coordinated motion reinforces the idea that the Great Attractor is not a singular destination but part of a larger flow pattern. Galaxies do not fall into it, they move across it, following the gentle descent of spacetime's curvature. Over billions of years, their paths will shift gradually, reflecting the deeper terrain of the universe. From our perspective on Earth, this motion is completely imperceptible. But telescopes reveal the truth: we are part of an enormous cosmic caravan traveling silently through the darkness. The motion is slow on human timescales but enormous on cosmic ones. Galaxies move at hundreds of kilometers per second, yet the distances between them are so vast that the motion feels glacial. In a human lifetime, a galaxy barely shifts. But across millions or billions of years, these subtle movements translate into sweeping journeys. The drift toward the Great Attractor is one such journey, slow, patient, but relentless. Like a river carving a canyon over ages, the accumulated effect becomes undeniable when viewed from enough distance or over enough time. This teaches us an important truth: the universe is not static, even if it appears so. Everything is moving. Everything is drifting. Everything is changing in ways too slow for any single generation to see. But perfectly clear when the cosmos is taken as a whole. A gravitational shadow hangs over the Hydra-Centaurus region. When astronomers mapped galaxy velocities and density fields, they found something like a gravitational shadow extending across the Hydra-Centaurus region. Not a literal shadow, but an area where motion patterns and mass distributions implied a deep gravitational influence. This gravitational shadow is the footprint of the Great Attractor, an invisible imprint detectable only through motion and gravitational lensing. It is the part of the universe where gravity bends space just a little more than average, causing galaxies to drift ever so gently toward it. Even though the visible light from this region is modest, its gravitational fingerprint is unmistakable. The region is extremely difficult to observe in visible light. The zone of avoidance hides more than just faint clusters. It also confuses observations. Stars from the Milky Way overlap with distant galaxies, making it challenging to distinguish foreground objects from background structures. Dust absorbs starlight, erasing the faintest galaxies entirely. This optical obscuration is why the Great Attractor remained hidden for so long. The technology of the 20th century simply wasn't capable of piercing the veil. Only with advances in infrared astronomy, radio surveys, and X-ray imaging did the region begin to reveal its true nature. What was once a blank patch of sky slowly transformed into one of the most complex and massive gravitational structures in the local universe. X-ray and radio observations reveal the hidden structures. Infrared surveys help see galaxies behind dust, but X-ray and radio wavelengths were the key to unlocking the deeper layers of the Great Attractor. X-ray telescopes revealed hot gas in massive clusters, including the Norma cluster, one of the most important components of the Great Attractor region. Radio surveys mapped neutral hydrogen in galaxies invisible in optical wavelengths. These techniques created a three-dimensional picture of the hidden structures, finally showing the clusters and filaments that produce the gravitational pull. Together, these observations allowed astronomers to reconstruct the region's true mass distribution, confirming what peculiar velocities had long suggested. The Great Attractor is a gateway to an even larger gravitational region. Perhaps the most surprising discovery about the Great Attractor is that it is not the deepest gravitational feature in the area. Beyond it lies an even larger, more massive structure, the Shapley Supercluster. As astronomers extended their surveys farther away, they found that the gravitational slope continues past the Great Attractor into Shapley's domain. This means galaxies are not flowing into the Great Attractor, but rather through it, moving along a pathway that leads deeper into the cosmic landscape. The Great Attractor is not the destination. It is the doorway. It is the edge of a vast gravitational valley. When taken together, all the clusters, filaments, dark matter concentrations, and peculiar velocities, the Great Attractor emerges not as a single object but as the rim of an enormous gravitational valley. Galaxies drift toward it not because it is the deepest point, but because it lies between us and an even greater gravitational basin beyond. This valley spans hundreds of millions of light-years, forming part of the structure we call Laniakea, the supercluster containing the Milky Way. The Great Attractor is one wall of this valley, a gentle slope guiding the motion of galaxies along the cosmic landscape. In this way, the Great Attractor becomes something beautifully understated. Not a monster, not a threat, but a quiet landmark in the terrain of the universe, one contour in a vast gravitational map that stretches far beyond our imagination. Hydra Centaurus is the first major galaxy complex linked to the Great Attractor. Long before astronomers understood the structure of the Great Attractor, they recognized an unusually massive region of galaxies stretching across the constellations Hydra and Centaurus. This region, known as the Hydra-Centaurus supercluster, became the earliest clue to the gravitational mystery affecting the Milky Way. It forms one of the densest concentrations of mass in our cosmic neighborhood, a gravitational continent in a universe shaped by invisible forces. Hydra Centaurus initially appeared to be the main candidate for the Great Attractor itself. Its clusters were large, its galaxies numerous, and its distribution suggested a significant gravitational influence. But as measurements deepened, astronomers realized this was only part of the story. Hydra Centaurus was not the final destination of the cosmic drift, it was only the outer shelf of a much deeper, hidden gravitational valley. Still, the region remains fundamental to our understanding of cosmic flows. It is the first major structure that reveals how the Milky Way and many neighboring galaxies are influenced by gravitational forces stretching across hundreds of millions of light-years. Inside Hydra Centaurus lie extremely dense structures. The Hydra Centaurus region is not a simple grouping of galaxies, it is a labyrinth of dense nodes, clusters, and filaments. Every part of it contains structures layered in complexity, galaxies spiraling around common centers, clusters merging slowly over billions of years, and dark matter halos weaving the silent framework beneath it all. These dense structures create powerful gravitational interactions. Some clusters contain thousands of galaxies, while others form elongated chains stretching through the darkness like cosmic rivers. The density is so high in certain areas that galaxies are locked in slow-motion dances, orbiting, merging, and warping one another's shapes through tidal forces. This extraordinary density is one reason Hydra, Centaurus plays such a large role in shaping the peculiar velocities of galaxies around it. It acts as one of the first major influences in the greater flow toward the deeper gravitational region that lies beyond. The Norma cluster, Abel 3627, is the central heart of the region. Among all the structures inside Hydra, Centaurus, one stands out as especially massive and gravitationally dominant, the Norma cluster, also known as Abel 3627. This cluster is often described as the gravitational heart of the Great Attractor region, not because it is the end of the flow, but because its mass forms a major part of the gravitational slope that guides the motion of surrounding galaxies. Norma contains thousands of galaxies and is enveloped by an enormous halo of dark matter. It sits at a crossroads of cosmic filaments that funnel galaxies and gas into its core. As these flows converge, Norma grows heavier, denser, and more influential over cosmic time. For decades, astronomers suspected that the key to the Great Attractor lay somewhere near Norma. They were right, but Norma was only the beginning of the story. Norma is gigantic but completely hidden behind the Zone of Avoidance. The Norma cluster is comparable in size and mass to famous clusters like Coma or Perseus, but unlike those luminous giants, Norma lies directly behind the Milky Way's thickest dust clouds. This unfortunate alignment means that Norma is almost invisible in optical light. Stars, gas, and dust from the Milky Way create a dense curtain that washes out distant galaxies, leaving only faint hints of light. For many years, astronomers didn't even know such a massive cluster existed. It was completely masked by the Zone of Avoidance, a region of the sky where visible light surveys cannot penetrate. Only with the advent of radio and X-ray astronomy did the Norma cluster finally emerge from behind the veil, revealing the true scale of the gravitational structures hidden there. X-ray observations reveal Norma's enormous mass. Unlike optical light, X-rays pass through the dust of the Milky Way. And when astronomers aimed X-ray telescopes toward the Hydra, Centaurus region, they immediately noticed something striking, an immense glow of hot gas surrounding a massive cluster. That glow belonged to the Norma cluster. Hot gas in galaxy clusters can reach tens of millions of degrees. It radiates in X-rays, allowing astronomers to estimate the cluster's mass. Norma's X-ray luminosity is staggering, comparable to some of the most massive clusters known. This indicates that Norma contains not just countless galaxies but also vast quantities of superheated gas, trapped by the cluster's deep gravitational potential well. Through X-ray eyes, Norma transforms from an invisible smudge into a blazing gravitational furnace, a hidden engine shaping the motion of galaxies across tens of millions of light-years. Dark matter makes up most of Norma's mass. As with most galaxy clusters, the visible matter in Norma, its stars and glowing gas, accounts for only a small fraction of its total mass. The majority of its gravitational power comes from dark matter, an invisible substance that neither emits nor absorbs light but dominates the mass budget of the universe. Gravitational lensing and X-ray measurements reveal that Norma's dark matter halo is enormous, extending far beyond its visible galaxies and forming a gravitational skeleton that holds the cluster together. Without dark matter, the cluster's hot gas would simply escape. Instead, it remains tightly bound, a silent testimony to the invisible mass shaping the region. This vast reservoir of dark matter is one of the key contributors to the gravitational slope we call the Great Attractor. Streams of hot gas show Norma is swallowing nearby galaxies. X-ray maps of the Norma cluster reveal streams and filaments of hot gas flowing inward, evidence that the cluster is actively accreting material. These gas streams originate from galaxies that venture too close to the cluster. As they fall toward Norma, their gas is stripped away by interactions with the dense intracluster medium. This stripping process heats the gas to millions of degrees, producing strong X-ray emission. It is a sign that Norma is still growing, still feeding, still pulling galaxies into its gravitational grasp. Over billions of years, this slow consumption will increase the cluster's mass even further, reinforcing its role as one of the primary structures within the Great Attractor region. Norma is comparable in mass to the famous Coma cluster, but much harder to see. The Coma cluster is one of the most studied galaxy clusters in the universe, bright, nearby, and easy to observe. Norma, on the other hand, is every bit as massive but far more difficult to detect because of the Milky Way's dust. If Norma were located away from the galactic plane, it would likely have been discovered decades earlier and celebrated as one of the major clusters in the local universe. Instead, its light struggles to reach us through thick layers of dust, making it a hidden giant, immense, influential, but largely invisible to optical telescopes. This invisibility is part of the Great Attractor's mystique, some of the universe's largest structures lie not in the clear night sky, but behind clouds of dust that hide them from view. Hydra, Centaurus and Norma together form a mid-level gravitational region. The combined mass of Hydra, Centaurus and the Norma cluster creates a substantial gravitational region, large enough to influence nearby galaxy groups and significantly contribute to the peculiar velocities observed in our cosmic neighborhood. However, as massive as this region is, it does not fully explain the observed bulk flow. The gravitational pull of Hydra, Centaurus accounts for part of the motion, but not all. The drift is too strong, too coherent, and extends across too wide an area to be explained solely by these structures. This realization marked a turning point. The Great Attractor could not be confined to Hydra, Centaurus alone. Something deeper lay beyond. But Hydra, Centaurus alone cannot explain the entire bulk flow. As astronomers measured the velocities of galaxies across broader regions, it became clear that Hydra, Centaurus and Norma, while massive, were not enough to generate the full gravitational pull affecting the Milky Way and its neighbors. The flow continued past Hydra, Centaurus, past Norma, past every structure that visible light surveys could initially detect. The implication was profound: a larger, deeper mass concentration, something even more powerful, must exist farther along the same direction. Hydra, Centaurus was only the beginning of the slope. This implies something much larger lies beyond. The failure of Hydra, Centaurus to explain the cosmic drift led astronomers to look even farther, beyond the zone of avoidance, past what optical telescopes could see. What they found, slowly and through painstaking surveys, was a gravitational titan, the Shapley Supercluster, containing some of the largest and most massive clusters in the local universe. The presence of Shapley meant that the Great Attractor was not a single gravitational well but part of a larger system. Hydra, Centaurus pulled us, yes, but Shapley pulled even harder from behind it. This layered structure transformed our understanding of the Great Attractor from a single region into a complex, cascading gravitational landscape. Infrared and radio surveys revealed a new map of the region. To see through the dust of the Milky Way, astronomers turned to infrared and radio astronomy. Infrared surveys like 2MASS and Dennis penetrated the dust veil, revealing galaxies previously hidden from view. Radio observations traced hydrogen gas in systems invisible to optical telescopes. With each new survey, the map of the Hydra-Centaurus region became clearer. Entire clusters emerged from the darkness. Filaments stretched across the zone of avoidance. Structures once thought sparse proved to be rich and interconnected. These deeper surveys provided the missing pieces, allowing astronomers to see the true mass distribution behind the Great Attractor's gravitational effect. Hundreds of hidden galaxies were discovered behind the dust. Before infrared and radio observations, the zone of avoidance seemed almost empty. But once new wavelengths were used, the region blossomed with galaxies, spirals, ellipticals, dwarfs, and entire groups that had been completely hidden. Some of these galaxies are part of the Norma cluster. Others belong to filaments stretching toward Hydra and Centaurus. Many of them form bridges that connect the Great Attractor region to even more distant structures like the Shapley concentration. It became clear that the darkness had deceived us. The region behind the Milky Way was not an empty void, it was a crowded, vibrant part of the cosmic web. The zone of avoidance no longer avoids us completely. Thanks to modern multi-wavelength astronomy, the zone of avoidance is no longer a complete mystery. While visible light still struggles to pass through it, infrared and radio signals reveal much of what lies behind the dust. We can now detect clusters, groups, and filaments hidden within the region. We can measure their redshifts, estimate their masses, and determine their role in the cosmic flow. The zone of avoidance still hides details, but it no longer blocks our understanding entirely. In a sense, technology has allowed us to lift the veil, slowly transforming a once forbidden region into one of the most fascinating and studied areas of the sky. Astronomers realized the visible region was only the tip of the iceberg. As hidden galaxies and clusters emerged from behind the dust, astronomers realized that everything previously mapped in Hydra, Centaurus represented only a fraction of the mass responsible for the Great Attractor. What they could see with optical telescopes was merely the illuminated portion of a vastly larger structure, just the tip of a cosmic iceberg buried under darkness and dust. The true mass, including dark matter and obscured clusters, extended far beyond initial estimates. This revelation shifted the entire perspective on the Great Attractor and the gravitational currents flowing through our cosmic neighborhood. Norma is only the first layer of a multi-layered system. As observations deepened, it became clear that the Norma cluster was not an isolated gravitational giant but part of a multi-layered structure. Behind Norma lie additional clusters, filaments, and the immense Shapley Supercluster, each contributing to the gravitational pull. The Great Attractor is not a single layer, it is a stack of gravitational structures, each adding depth to the cosmic valley. Norma is simply the frontmost layer visible to our instruments, with many more lying farther out. Uneven mass distribution makes finding a true center impossible. Because the Great Attractor is not a single object but a region composed of many clusters and dark matter halos, there is no precise center to point to. Gravity is spread across filaments, nodes, and sheets. Some parts pull more strongly than others. This uneven distribution means the gravitational center shifts depending on how far one looks and which structures are included. The idea of a central point gives way to a broader understanding. The region is a slope, not a pit, a gravitational gradient, not a beacon. Gravity is not concentrated in one spot. Unlike objects such as stars or black holes, the Great Attractor's gravity is diffuse. It arises from enormous volumes of space filled with clusters, galaxies, and dark matter. Not from a compact singularity. This distributed mass creates a smooth gravitational field across tens of millions of light-years. Because the gravity is spread out, galaxies do not fall toward a single point but instead drift along multiple pathways toward regions of slightly lower gravitational potential. This behavior reflects the true nature of cosmic structure formation, where gravity acts as a sculptor shaping vast, interconnected landscapes. The entire region forms a wide gravitational slope, not a deep hole. A deep gravitational hole would pull galaxies inward sharply, producing violent infall patterns. But the Great Attractor does nothing of the sort. Instead, it forms a wide, shallow slope, one that nudges galaxies gently over billions of years. This slope extends from the local group through Hydra, Centaurus and onward toward Shapley. It is part of the broader basin that defines our home supercluster, Laniakea. Galaxies, including the Milky Way, simply follow the natural contours of this vast gravitational landscape. The Great Attractor is truly a region, not a point. All evidence, from velocities, from X-rays, from radio surveys, from multi-wavelength mapping, points to one conclusion: the Great Attractor is not a single object but a region of enhanced density stretching across millions of light-years. It is a gravitational environment shaped by layers of clusters, filaments, and dark matter. It influences galaxies not through a single pull but through a distributed slope. It is an extended structure, a piece of the cosmic web rather than a solitary giant. Understanding this transforms the Great Attractor from a mysterious thing into a natural part of the universe's grand architecture, a quiet gravitational plateau guiding the drift of galaxies through the deep cosmic night. Dark matter makes up 85% of the mass in the Great Attractor region. When astronomers estimate the mass contained in the Great Attractor region, one truth stands out above all: most of its mass is invisible. Roughly 85% of the gravitational pull comes from dark matter, a mysterious, unseen substance that neither emits nor absorbs light. The luminous galaxies, shining clusters, and glowing X-ray gas clouds account for only a fraction of what is truly there. This dominance of dark matter explains why the region's gravitational influence is far greater than its visible light suggests. We observe galaxies drifting toward the Great Attractor with tremendous velocity, yet when we look at the visible matter alone, the numbers simply don't add up. Only by including the vast reservoirs of dark matter can the gravitational strength of the region be fully explained. It is not the shining stars that sculpt this cosmic movement, but the invisible mass beneath them. Without dark matter, the Great Attractor would not exist. If the universe contained only the matter we can see, the stars, dust, gas, and galaxies, the Great Attractor would be far too weak to influence thousands of galaxies. It might not even exist as a significant gravitational feature. Dark matter is the substance that deepens the gravitational basin. It fills the cosmic web like mortar between stones, binding structures together and amplifying their pull. Without it, Hydra, Centaurus would merely be a moderate cluster system. The Norma cluster would be impressive, but not powerful enough to redirect entire superclusters. Dark matter is the essential ingredient. Remove it, and the gravitational valley flattens. Keep it, and the universe becomes a landscape full of slopes, ridges, and currents, one of which we call the Great Attractor. Visible matter is only a thin shell wrapped around dark matter. Structures. When we look at a galaxy in the sky, we are seeing only its glowing skin. The stars, gas, and dust represent a small portion of the galaxy's true substance. Beneath that shining shell lies a vast dark matter halo, an enormous structure that does not glow but provides most of the galaxy's mass and gravitational stability. The same is true for the entire Great Attractor region. Every cluster and group of galaxies sits inside massive dark matter halos. These halos overlap, merge, and interconnect to form enormous gravitational scaffolding. The bright galaxies we observe are merely the lanterns decorating the surface of a much deeper, invisible structure. To understand the Great Attractor, one must look not at the light, but at the shadow beneath the light, a dark architecture shaping the universe from below. Galaxies move not because of what we see, but because of what we don't see. Our eyes are drawn to the luminous parts of the cosmos, stars shining in spirals, clusters glowing in X-rays, galaxies forming elegant patterns. But gravity does not care about radiance. Galaxies follow the pull of mass, whether that mass glows or not. The peculiar velocities we observe, the sideways drifts, the long gravitational flows, are shaped by the invisible distribution of dark matter. The Milky Way moves not because a bright object pulls it, but because an enormous, unseen halo or filament of dark matter creates a gravitational slope beneath it. In this way, dark matter becomes the true architect of cosmic motion. The universe is luminous. Parts are only markers sprinkled along its invisible paths. Dark matter forms giant halos stretching tens of millions of light-years. Dark matter does not cluster tightly like stars or planets. Instead, it spreads across vast regions, forming enormous halos that can envelop entire clusters of galaxies. These halos stretch tens of millions of light-years, creating gravitational envelopes far larger than any luminous structure. In the Great Attractor region, several such halos overlap: the halo of Hydra, Centaurus, the immense halo of the Norma cluster, and additional halos belonging to filaments and subclusters. Each one deepens the gravitational landscape. Together, they form a continental scale structure that shapes the flow of galaxies across the region. These halos are too large and too diffuse to see, but they leave undeniable fingerprints on the motion of everything within their reach. Overlapping halos create the deep gravitational slope of the Great Attractor. When dark matter halos overlap, their gravitational effects combine. Instead of competing, they merge seamlessly into a larger, smoother gravitational field. In the Great Attractor region, this overlapping of halos creates a profound gravitational slope, one broad enough to influence entire superclusters. This slope is not a sharp pit but a gentle descent that extends across hundreds of millions of light-years. Galaxies slide along it slowly, responding to the combined pull of dark matter and Hydra, Centaurus, Norma, and beyond. The more halos overlap, the deeper the slope becomes. This is why the Great Attractor is so powerful despite its faint luminosity. Its true mass lies in the invisible structures layered beneath the visible ones. The pull comes from invisible mass, not from light. Light is a storyteller but not a ruler. Gravity alone governs the motion of galaxies. And gravity depends on mass, not on brightness. For this reason, the luminous stars in a region can be misleading. A faint cloud of dark matter can outweigh a glowing cluster 1,000 times brighter. In the Great Attractor region, the majority of the gravitational force arises from dark matter. The bright clusters are like candles on the surface of a massive, invisible mountain. They help us see where the peaks are located, but they do not define the mountain's true shape. The galaxies move not toward light, but toward mass. And most of that mass is dark. Galaxy velocities make sense only when dark matter is included in models. Before the concept of dark matter was introduced, the speeds of galaxies simply didn't make sense. In clusters, galaxies moved so quickly that they should have flown apart long ago if only visible matter were holding them together. The same was true on larger scales. The peculiar velocities of galaxies could not be explained by luminous mass alone. When dark matter is added to gravitational models, everything suddenly fits. Galaxies move at the right speeds. Clusters remain bound. The Great Attractor exerts the expected pull. The drift of the Milky Way becomes consistent with the mass distribution inferred from multi-wavelength observations. Dark matter is not a patch, it is the missing foundation that makes the universe's motions understandable. Gravitational lensing maps reveal far more mass than visible light suggests. Gravitational lensing, the bending of light by mass, offers a direct way to detect dark matter. When astronomers map the distortions in background light caused by clusters in the Great Attractor region, the results are astonishing. The mass inferred from lensing is several times larger than what can be seen in stars and gas. This means the clusters and filaments in the region are wrapped in enormous cocoons of dark matter. These lensing measurements serve as some of the strongest evidence that the Great Attractor's influence comes from an invisible backbone of mass, not from the luminous galaxies themselves. Through lensing, dark matter reveals its shape without ever showing its face. Dark matter forms the backbone of the Great Attractor. Every major structure in the Great Attractor, Norma, Hydra, Centaurus, their filaments, and the surrounding clusters, rests upon a foundation of dark matter. This foundation forms the true skeleton of the region. The luminous galaxies merely trace its outline like dewdrops on spider silk. Without dark matter, the Great Attractor would be a loose collection of clusters. With dark matter, it becomes a coherent gravitational basin, capable of guiding the motion of entire superclusters. Dark matter is the framework that holds the region together, just as bones support the body beneath the skin. Dark filaments connect Hydra, Norma, and beyond. Filaments of dark matter act as the highways of the universe, connecting clusters and guiding the formation of galaxies. These filaments weave together Hydra, Centaurus, Norma, and the structures extending farther toward the Shapley Supercluster. Galaxies embedded in these filaments move along them like water flowing through river channels. Gas is funneled inward. Smaller clusters merge. The entire structure grows over time. These dark filaments form the connective tissue of the cosmic web, and the Great Attractor is one of their major junctions, a convergence point of invisible paths. Galaxy flows mirror the flows of dark matter. Galaxies behave like tracers floating in a fluid. They drift along the gravitational contours created by dark matter. Their peculiar velocities reflect the underlying distribution of dark matter, not the distribution of light. This is why the motion of thousands of galaxies points toward the Great Attractor even though the region is not exceptionally bright. The galaxies are following the dark flow, shaped by the deep gravitational slopes of overlapping dark matter structures. Where dark matter flows, galaxies follow. Always. Dark matter does not interact with light and is completely invisible. Dark matter's most defining feature is its invisibility. It does not emit light. It does not absorb it. It does not scatter it. To telescopes, it is as clear as empty space. Yet its gravitational pull is unmistakable. Dark matter bends light around it, shapes the orbits of galaxies, and sculpts the cosmic web. It exists everywhere, affecting everything, while remaining hidden from direct observation. In the Great Attractor region, the inability to see dark matter directly made the gravitational puzzle especially difficult. Only through motion, lensing, and high-energy observations could astronomers uncover its presence. Galaxies follow dark matter the way water follows a riverbed. If you picture dark matter as the riverbed of the universe, galaxies become the water that flows across it. They follow the contours carved by dark matter's distribution. They drift along its slopes and settle into its basins. The Milky Way, along with countless others, is sliding along a dark matter channel that leads through Hydra, Centaurus and onward to the Shapley Supercluster. This invisible river guides entire galaxy groups as surely as gravity guides a waterfall. The universe's shape is not determined by starlight but by the silent geometry of dark matter underneath. Cosmological simulations reproduce the Great Attractor only when dark matter is included. When scientists run simulations of the universe based solely on visible matter, no Great Attractor forms. There is no deep gravitational basin, no coherent flow. No large-scale drift resembling what we observe. The universe remains too smooth, too shallow, and too weakly structured. But when dark matter is included, everything changes. Clusters form where they should. Filaments stretch in the right directions. The Hydra-Norma region emerges as a significant gravitational basin. The Shapley Supercluster appears at the far end of a deep slope. Only with dark matter do the simulations replicate the real cosmic flows we measure today. Without dark matter, no gravitational basin would exist. A gravitational basin is created when mass accumulates in a region large enough to bend spacetime into a broad, downhill slope. Without dark matter, the mass in Hydra, Centaurus and Norma would be far too little to shape the cosmic landscape in a meaningful way. The basin we call the Great Attractor owes its existence to dark matter's vast and silent presence. Visible matter enhances the slope but does not define it. Dark matter is the matter. It is the silent sculptor, shaping the cosmic web long before galaxies formed. Its slow, inexorable pull guided the first pieces of matter into place shortly after the Big Bang. In the Great Attractor region, dark matter's artistry is particularly clear. The complex gravitational landscape, Norma, Hydra, Centaurus, and the pathways toward Shapley, was carved by the invisible hand of dark matter. Luminous matter merely settled into the form already laid out for it. Peculiar velocity is direct evidence of dark matter's influence. The sideways drift of galaxies, peculiar velocity, is one of the strongest signs that dark matter exists. The magnitude and coherence of these velocities cannot be explained by luminous matter alone. Only with vast quantities of dark matter do the observed motions make sense. The Great Attractor region demonstrates this beautifully. The peculiar velocities point directly toward regions rich in dark matter, revealing the gravitational terrain even when the light is hidden. The Great Attractor is just one shadow of a much larger dark matter network. The Great Attractor is not a standalone mystery. It is one node in a vast web of dark matter structures stretching across the universe. Beyond it lies the Shapley Supercluster, another massive convergence point of dark matter. Together, they form part of Laniakea, a gravitational basin defined not by light, but by dark matter distribution. The more deeply we map the cosmos, the more we see that the Great Attractor is simply one ridge, one slope, one contour in a much larger, invisible world. The dark universe shapes every motion we observe. The luminous universe, the one we see with telescopes, is only a faint outline of a much larger, darker universe beneath it. Every galaxy's drift, every cluster's orbit, every large-scale flow is shaped by the distribution of dark matter. The Great Attractor itself is a testament to this truth. Its gravitational influence, vast and powerful, comes almost entirely from matter we cannot see. Yet everything moves in response to it. In this way, dark matter becomes the quiet, unseen heart of cosmic motion, the soul of the universe's architecture, guiding galaxies gently along invisible paths in the deep, silent night. The zone of avoidance hides 15 to 20% of the entire sky. When astronomers first tried to map the universe, they encountered a frustrating blank spot, an enormous swath of the sky where almost nothing beyond our galaxy could be seen. This region came to be known as the Zone of Avoidance. And it hides between 15% and 20% of the entire celestial sphere. Imagine trying to draw a world map with a fifth of the continents missing. That was the challenge astronomers faced for more than a century. This hidden portion of the sky obscured everything behind it, galaxies, clusters, filaments, and even some of the most massive structures in the local universe. The absence was not due to emptiness but to overwhelming foreground interference from our own Milky Way. For decades, it stood as one of astronomy's largest blind spots, shaping not only what we could see but also what we thought existed. Because, dust, gas, and dense star fields in the Milky Way's disk. The zone of avoidance exists because we live inside the Milky Way, embedded in a disk rich with stars, gas clouds, and lanes of interstellar dust. These materials scatter and absorb visible light, forming a thick, glowing curtain across the sky. The dust especially is an efficient blocker, tiny grains that extinguish starlight from galaxies millions of light-years away. Along the galactic plane, star fields are so crowded that individual points of light blend together, overwhelming the faint signals from distant galaxies. Even large clusters are drowned out by the brightness of local stars. To an optical telescope, this region appears luminous and chaotic, but its brightness hides a deeper darkness, the universe beyond. Visible light from background galaxies is almost completely blocked. Galaxies shining behind the galactic plane send their photons toward Earth, but those photons must travel through the Milky Way's dusty midplane. Most never make it. Dust grains absorb and scatter nearly all visible wavelengths, turning brilliant spiral galaxies into faint smudges or erasing them entirely. For a long time, astronomers thought these regions were nearly empty because their telescopes showed only foreground stars. The truth was the opposite. The zone of avoidance was hiding a bustling, crowded realm full of structures as rich as any other part of the sky. The light was there. It simply couldn't get through. It was once a blank region on cosmic maps. Early sky surveys showed the universe with a massive void running along the Milky Way, a mysterious blank strip where galaxies seemed to vanish. This blankness wasn't due to actual cosmic emptiness but to observational limitations. Still, it created the illusion that part of the universe might be sparsely populated. Astronomers called it a zone to avoid because mapping it was nearly impossible. It was the cosmic equivalent of uncharted territory, mysterious, inaccessible, and filled with speculation. Only later would humanity learn that behind that empty strip lay some of the most important hidden structures in our local universe. The Great Attractor lies directly behind this dusty curtain. One of the greatest cosmic coincidences, or cosmic frustrations, is that the Great Attractor sits exactly behind the densest part of the Zone of Avoidance. This unfortunate alignment meant that for decades, no visible light telescope could reveal its structure. Astronomers could sense a gravitational pull, could measure the motion of galaxies, but could not yet see the source. The universe placed one of the largest nearby mass concentrations behind the thickest layer of our galaxy's dust, turning a major gravitational feature into a near-invisible phantom on astronomical maps. It was as if a mountain had been hidden behind clouds for centuries. This is why the Great Attractor was invisible for so many decades. The reason the Great Attractor remained a mystery for so long was not a lack of mass or importance, it was simply concealed behind one of the most impenetrable regions of the night sky. Even though its gravity affected thousands of galaxies, its light could not reach us. Astronomers were forced to detect it not through images but through motion, through the peculiar velocities of nearby galaxies and the drift revealed by the cosmic microwave background. Its invisibility was a product of perspective. The Great Attractor was always there, but the galaxy we inhabit blocked it from view. Only radio and infrared wavelengths can pierce the dust. While visible light is blocked by dust, radio waves and infrared light pass through much more easily. This is because their longer wavelengths are not scattered by small dust grains. Once radio and infrared astronomy matured, the zone of avoidance began to open. Infrared surveys could reveal the faint glow of stars in obscured galaxies. Radio telescopes could detect the hydrogen gas inside galaxies hidden from optical view. These wavelengths became essential tools for mapping what lies beyond the Milky Way's curtain. X-rays reveal the hot clusters behind the darkness. X-ray observations added another crucial piece to the puzzle. Hot gas in galaxy clusters emits copious X-rays, and these energetic photons can also penetrate the Milky Way's dust much more effectively than visible light. When astronomers pointed X-ray telescopes through the zone of avoidance, they discovered bright knots of high-energy emission, signatures of massive clusters hidden behind the dust. One of the most important discoveries was the Norma cluster, whose glowing X-ray halo announced a gravitational titan previously invisible in optical wavelengths. The Norma cluster is visible only in X-ray, not in optical light. Optical telescopes see almost nothing in the direction of the Norma cluster, only a dense field of stars from the Milky Way. But in X-rays, Norma blazes with intensity. Its hot gas, reaching tens of millions of degrees, shines brightly in high-energy wavelengths that pierce the dust. This discovery confirmed that enormous structures were hidden in the zone of avoidance. The absence of light in optical observations was not an absence of structure. It was a veil obscuring a galaxy cluster as massive as the famous Coma cluster. Radio surveys allow redshift measurements of hidden galaxies. In visible wavelengths, galaxies behind the zone of avoidance simply disappear. But radio telescopes can detect the 21-centimeter emission from neutral hydrogen gas inside them. This emission passes through dust easily, allowing astronomers not only to detect hidden galaxies but also to measure their redshifts, their distances and velocities. Through radio surveys, astronomers reconstructed a large-scale map of galaxy motions and discovered entire groups and filaments behind the galactic plane. These measurements helped reveal the true gravitational landscape that light alone could not uncover. Infrared surveys like 2MASS opened a new map of the region. The 2-micron all-sky survey, 2MASS, was a turning point in our understanding of the zone of avoidance. Using infrared wavelengths, 2MASS was able to see through the dust and detect tens of thousands of galaxies previously unknown. These observations revealed the hidden structures around the Great Attractor, clusters, filaments, and bridges connecting major superclusters. 2MASS transformed that empty zone into a richly populated region, altering our understanding of local cosmic geography. The zone of avoidance is no longer avoiding us. Thanks to radio, infrared, and X-ray surveys, the zone of avoidance is no longer a cosmic blind spot. While optical observations still struggle, multi-wavelength astronomy has allowed us to penetrate the dust and reconstruct a detailed map of what lies behind. Today, the zone of avoidance is one of the most studied and data-rich regions of the sky, not because it is easy to observe, but because it contains essential clues to the gravitational forces shaping our galaxy's motion. Hidden clusters are revealed layer by layer. As different wavelengths peeled back the darkness, astronomers found that the Great Attractor region is not a single cluster, but multiple layers of structures. First came the Norma cluster, then surrounding groups, then extended filaments, then deeper clusters beyond Norma. Each new survey revealed another layer of structure previously masked by dust. The Great Attractor transformed from a mysterious gravitational anomaly into a detailed cosmic landscape. The Great Attractor turned out to be many structures, not one. Originally, astronomers imagined the Great Attractor as a single, massive cluster. But as multi-wavelength data accumulated, it became clear that the gravitational pull came from a complex network of structures: Hydra cluster, Centaurus cluster, Norma cluster, smaller groups, and extended dark matter filaments. The Great Attractor is not a single mountain, it is a mountain range. The asymmetry of the zone made astronomers think there was only one pulling source. Because visible light revealed almost nothing behind the Milky Way, astronomers initially assumed the gravitational pull must come from a single, dominant structure hidden behind the dust. In reality, the region is profoundly asymmetric, filled with overlapping clusters and filaments. The illusion of a single object arose because the dust blocked the more distant structures, leaving only partial clues visible. Once infrared and radio observations filled in the missing pieces, the true complexity of the region emerged. The region is a junction of multiple dark matter filaments. Far from being an isolated structure, the Great Attractor region is a cosmic crossroads, a junction where multiple dark matter filaments converge. These filaments act like highways carrying galaxies and gas across cosmic distances. Their convergence creates a natural gravitational basin. This dense web of filaments explains why so many galaxies drift toward the region. They are following the underlying dark matter network that shapes the cosmic web. It is a secret corridor leading toward more distant structures. When astronomers mapped the deeper regions behind the zone of avoidance, they discovered that the Hydra, Centaurus, Norma complex is not the final destination of the cosmic flow. Instead, it forms a corridor leading toward even larger structures farther away, especially the Shapley Supercluster. The Great Attractor is not the end of the river. It is the channel through which the river flows. The zone of avoidance once hid the true nature of the Great Attractor. Because so much of the region was invisible, early theories about the Great Attractor were incomplete. Astronomers underestimated the mass, misunderstood the structure, and misinterpreted the gravitational flow. The dust veil concealed the deeper filaments and clusters that now form our modern understanding. The zone of avoidance hid vital clues, delaying the discovery of the Shapley Supercluster and the realization that the Great Attractor is only a midpoint in a much larger gravitational landscape. Today it is no longer a forbidden region. With modern technology, the zone of avoidance is no longer a place astronomers avoid, it is a gateway to discoveries. Multi-wavelength surveys have turned the region into a dense mosaic of data points. What was once avoided is now explored with enthusiasm, revealing the universe's hidden architecture. The dust still blocks visible light, but it no longer blocks understanding. Lifting the curtain was the key to finding the Shapley Supercluster. Only after astronomers penetrated the dust veil of the zone of avoidance did they realize that the true gravitational powerhouse driving the cosmic flow was not Hydra, Centaurus or Norma alone, but the far more massive Shapley Supercluster lying beyond. The zone of avoidance was the curtain. Behind it lay the doorway to one of the largest structures in the nearby universe. Peculiar velocity is measured by comparing true redshift and expansion redshift. At first glance, a galaxy's redshift tells us how fast it is moving away due to the expansion of the universe. But redshift is a blend of two ingredients, cosmic expansion and the galaxy's own motion through space. Peculiar velocity is the difference between these two values. To measure it, astronomers estimate how much redshift would arise purely from the expansion of the universe at that galaxy's distance. Then they subtract that from the observed redshift. The leftover motion, sometimes toward us, sometimes sideways, sometimes faster than expansion alone, reveals the galaxy's true gravitational drift. This drift carries the whispers of hidden structures, dark matter peaks, filaments, and basins that bend spacetime. Peculiar velocity might seem like a subtle residual, a small leftover from a huge calculation, but it holds immense power. It is the quiet language through which galaxies reveal what gravity is doing behind the scenes. It is one of the most important tools for detecting the Great Attractor. The Great Attractor was discovered not through photographs or bright clusters, but through peculiar velocity measurements. These velocities showed a pattern: galaxies across enormous distances were moving slightly sideways relative to what pure cosmic expansion predicted. This sideways drift was the first clue that something massive was pulling on them. The motion pointed consistently toward the Hydra, Centaurus region, even when visual observations showed nothing extraordinary there. Because peculiar velocity responds directly to gravity, not to brightness. It became the key detective in revealing the invisible mass hidden behind the Milky Way's dust. Without peculiar velocity, the Great Attractor might have remained a mystery far longer, or mistaken for something much smaller. The farther a galaxy is, the more reliable its velocity data becomes. Surprisingly, the galaxies farthest away often give the clearest peculiar velocity data. At large distances, the expansion of the universe dominates their redshift. Because expansion provides such a strong baseline signal, any deviations from it stand out more clearly. Nearby galaxies, in contrast, have motions affected by many small, local gravitational tugs: the Milky Way, the Local Group, the Virgo Cluster, nearby voids. Their peculiar velocities blend together like ripples in a small pond. But distant galaxies reveal the broad, slow-moving currents, the large-scale gravitational flows that span hundreds of millions of light-years. This is why the motion toward the Great Attractor became unmistakable only when astronomers extended their surveys farther into deep space. Peculiar velocity creates an indirect map of gravity. Where visible light fails, peculiar velocity succeeds. Using the motions of galaxies, astronomers can create maps of gravitational influence, even when the mass responsible for that influence remains hidden. Galaxies move like test particles. Their velocities trace the shape of spacetime itself. By plotting these motions, astronomers can draw the contours of gravitational basins, shallow slopes, deep valleys, wide plateaus. Peculiar velocity becomes a kind of topographical tool, revealing the terrain of the invisible universe. This method is powerful precisely because gravity cannot hide. Light can be blocked by dust or absorbed by gas, but gravity always leaves fingerprints in motion. Galaxies near the Great Attractor move in similar directions. When astronomers mapped the motions of galaxies around Hydra, Centaurus and Norma, a striking pattern appeared. These galaxies leaned toward the same region, following similar trajectories. They were not random. They were not scattered. They flowed together. This collective motion is one of the strongest signatures of a gravitational basin. Galaxies respond to the underlying structure of dark matter. When many galaxies move in consistent ways, it means they are sliding down the same gravitational slope. The closer they are to the Great Attractor, the more aligned their motions become. Some galaxies move even faster than expected. In the region around the Great Attractor, a few galaxies move noticeably faster than models predicted. These overachieving velocities are not mistakes, they are signs of a deeper gravitational influence. When a galaxy accelerates beyond the expected drift, it means it is falling into a steeper gravitational gradient, closer to a denser concentration of dark matter or approaching a junction of filaments. These galaxies act like warning signs. There is something deeper here. This is one of the clues that made astronomers suspect the Great Attractor was not the final destination of the flow. Faster velocities reveal galaxies sliding down a deeper gravitational slope. The galaxies that move faster are like raindrops sliding more quickly down a steep roof. Their enhanced velocity tells astronomers that the gravitational terrain becomes deeper as one moves farther along the flow. This deepening slope eventually pointed toward a larger structure beyond Hydra, Centaurus, the Shapley Supercluster. The accelerated galaxies revealed a truth hidden behind dust and distance. The Great Attractor is not a pit, it is the beginning of a downhill path leading to something far more massive. 3D maps of peculiar velocity show a massive global flow. When astronomers compiled a full three-dimensional map of galaxy motions, not just their redshifts, but their genuine drifts through space, a breathtaking structure emerged, a vast, coherent flow involving thousands of galaxies. The Milky Way, the Virgo cluster, Hydra, Centaurus, Norma, all were part of the same immense stream. It wasn't a chaotic scatter of individual motions. It was coordinated, sculpted, almost rhythmic. This 3D map became a revelation. It showed that the universe around us is not static or random but filled with cosmic rivers that guide galaxies gently across the void. The flow does not end at the Great Attractor. At first, astronomers assumed the flow would converge at the Great Attractor. That would have been simple: galaxies fall in, the flow ends, the mystery solved. But that was not what the data showed. Instead, the flow passed through the Great Attractor. Peculiar velocities did not decrease there, they continued smoothly beyond it. The direction of motion did not terminate, it extended farther outward. This was the moment scientists realized the Great Attractor was not a final destination but a checkpoint along a much longer gravitational descent. The motion continues toward the enormous Shapley Supercluster. As maps extended farther, peculiar velocities kept pointing toward a monumental structure deeper in space, the Shapley Supercluster, one of the most massive superclusters in the local universe. Shapley's gravitational field dwarfs that of Hydra Centaurus. It is so massive that it creates a large-scale flow extending hundreds of millions of light-years. The Great Attractor contributes to the motion, but Shapley dominates it. This deeper, more powerful target explains why galaxies never stop at the Great Attractor, they are on a path toward Shapley's vast gravitational well. These observations forced scientists to expand the map of the universe. Early cosmic maps ended at the edge of the Zone of Avoidance and the Hydra Centaurus region. But the peculiar velocity data demanded something more. The gravitational forces implied by the flow were simply too large to be explained by local clusters. Astronomers had to push surveys deeper, build more sensitive telescopes, and use non-optical wavelengths to peer through dust. These efforts expanded our cosmic map, revealing layers of structure previously invisible. The universe grew bigger, not in size, but in discovered complexity. Galaxy clusters beyond the Great Attractor fit the downhill motion pattern. When the deeper regions behind the Great Attractor were finally mapped, the galaxy clusters found their showed velocities perfectly consistent with a gravitational slope continuing toward Shapley. This consistency confirmed the earlier suspicion, the Great Attractor is only a midpoint. The motion of galaxies matches exactly what would occur if they were sliding across a vast gravitational landscape whose deepest point lies far beyond norma. Peculiar velocity reveals the shape of the gravitational basin. Just as water reveals the shape of a valley by the way it flows, peculiar velocity reveals the shape of gravitational terrain. By tracing the movement of galaxies, astronomers can see where the slopes begin, where they steepen, and where they converge. This creates a gravitational contour map of the universe, one that shows the basins, ridges, and pathways carved by dark matter. In this map, the Great Attractor appears not as a point but as a wide depression, the beginning of a more massive, deeper basin stretching toward Shapley. It is the only way to see mass hidden behind dust. Visible light can be blocked. Even infrared can struggle. But gravity cannot hide. Peculiar velocity is one of the only tools capable of revealing mass distributions behind opaque regions like the Zone of Avoidance. By observing how galaxies drift, astronomers can map structures that no telescope can image directly. Peculiar velocity becomes a form of cosmic echolocation, a way of sensing hidden mass through the motion of nearby objects. The Great Attractor is not the final goal of the flow. Once peculiar velocity maps reached beyond Hydra Centaurus, the story changed. The flow did not converge at the Great Attractor. It continued onward, deeper into the cosmic web. This was a paradigm shift. The Great Attractor was not the gravitational heart of the region. It was merely a slope along the path toward Shapley. Its role was still important, but it was not the ultimate cause of the motion. The Great Attractor is only the first segment of a much larger slope. With the full peculiar velocity data, Astronomers saw that the gravitational terrain forms a long, continuous descent from the local group through Virgo, Hydra, Centaurus, Norma, and eventually into the Shapley concentration. The Great Attractor is the first bend in that descent, a gravitational terrace along a far deeper valley. Understanding this reshaped the entire concept of cosmic flow. Velocity field maps reveal a broad dip in spacetime. When the velocities are plotted in 3 dimensions, a broad gravitational dip appears, stretching from our position all the way to Shapley. The dip is not sharp or narrow. It is wide, smooth, and gradual, like a valley carved by the unseen hand of dark matter. This gravitational dip shapes the motion of everything in its vicinity. The Great Attractor is one of the major contours along this valley. That dip leads directly to the Shapley Supercluster. All lines of flow, when extended far enough, converge toward Shapley. It is the deepest part of the gravitational basin, the true center of mass influencing the region on the largest scales. The Great Attractor is simply the gateway to this deeper descent. It marks the point where the gravitational slope begins to steepen toward Shapley's colossal mass. Shapley is the deepest part of the basin. Measurements confirm that Shapley contains more mass than any other nearby structure, including Hydra, Centaurus, and Norma. It is the true gravitational anchor of the local universe. The peculiar velocities of galaxies match perfectly with a model in which Shapley sits at the bottom of the basin, drawing galaxies from hundreds of millions of light-years away. Peculiar velocity is the compass of the entire journey. Through dust, distance, and darkness, peculiar velocity guided astronomers across the cosmic landscape. It pointed the way to Hydra, Centaurus, then Norma, then beyond, ultimately revealing the immense gravitational continent dominated by Shapley. Peculiar velocity is the compass of the dark universe. A silent guide showing where mass truly lies, and how galaxies drift across the unseen terrain of spacetime. Shapley is the largest supercluster known near the Milky Way. Among all the structures in our cosmic neighborhood, the Shapley Supercluster stands unmatched. It is the most massive concentration of galaxies within a few hundred million light-years, a gravitational titan, towering over the nearby universe. While other superclusters such as Virgo or Hydra, Centaurus are impressive, Shapley makes them look modest by comparison. Its scale is staggering, tens of thousands of galaxies woven together into an enormous gravitational tapestry. Shapley's immensity makes it the dominant force shaping the flow of galaxies across our region of the cosmos. It is not just a large supercluster, it is the supercluster, the gravitational crown of our local universe. Everything near it, including the Milky Way, feels its pull. Its mass far exceeds that of Hydra, Centaurus. The Hydra-Centaurus region, which forms part of the Great Attractor, is massive in its own right. But Shapley surpasses it many times over. Estimates suggest that Shapley contains an order of magnitude more mass than Hydra, Centaurus, making it easily one of the densest local structures known. While Hydra, Centaurus shapes the early slope of our gravitational descent, Shapley deepens that slope dramatically, pulling galaxies from hundreds of millions of light-years away. This difference in mass explains why peculiar velocities continue past the Great Attractor and increase as they approach Shapley. Shapley contains dozens of enormous galaxy clusters. Shapley is not a single cluster but a vast assembly of clusters, dozens of them, each containing hundreds to thousands of galaxies. These clusters vary in size, shape, and evolutionary stage, but collectively they form an interconnected network of extraordinary density. Clusters like Able 3558, Able 3562, and Able 3571 are among the most notable members of the Shapley concentration. Each one is a gravitational city, filled with galaxies swirling around their shared center of mass. Combined, they create a landscape of staggering depth. Many of its clusters contain thousands of galaxies. Individual clusters within Shapley rival or exceed iconic clusters. Like Coma. Sun contain more than 1,000 galaxies, giant ellipticals, spirals, lenticulars, and countless dwarfs. The amount of luminous matter is breathtaking, but the true mass remains mostly dark. These clusters interact, merge, and collide over cosmic timescales, generating vast amounts of hot gas and producing strong X-ray emission. The cluster cores are so dense that galaxies constantly influence one another, warping their shapes through tidal forces and gravitational encounters. This rich and crowded environment is why Shapley exerts such tremendous gravitational influence across the cosmic web. Shapley lies farther away than the Great Attractor but exerts a stronger influence. The Shapley Supercluster sits much farther from the Milky Way than the Great Attractor. Yet its gravitational effect is far stronger. Distance does not diminish its impact because its mass is so colossal. Imagine a mountain far larger than any nearby hill, even from afar. Its slope determines the direction of the river. Shapley is that distant mountain. Its vast gravitational valley pulls galaxies across enormous distances, dominating the motion of our region of the universe. This is why peculiar velocities continue increasing beyond Hydra, Centaurus. They are being shaped by something bigger, deeper, and farther away. Shapley is the primary cause of the bulk flow. While the Great Attractor contributes to the bulk flow, it is not the primary driver. Shapley, with its monstrous mass and extended network of clusters, is the true engine behind the galaxy-wide drift. Simulations and observations agree, galaxies in our region are moving along a gravitational descent that ultimately leads to Shapley. The Great Attractor tilts the slope, but Shapley deepens it. Its gravitational well stretches across hundreds of millions of light-years, steering the motion of entire superclusters, including our own Laniakea. The Great Attractor is only a waypoint on the road to Shapley. Once astronomers realized that the bulk flow did not converge at Hydra, Centaurus, they understood that the Great Attractor was merely a gravitational waypoint. It marks the first bend in the cosmic slope, a passing point on a much longer journey toward Shapley. Galaxies drift into the Great Attractor region not to stop but to continue their descent. It is like cresting a hill only to see a deeper valley ahead. The true endpoint of the cosmic flow lies beyond the dust, beyond Norma, beyond Hydra, Centaurus, deep within Shapley. The flow of galaxies does not end at Norma, it passes through it. The Norma cluster, once thought to be the gravitational core of the Great Attractor, does not halt the cosmic drift. Galaxies do not spiral into Norma nor slow as they approach it. Instead, their velocities remain consistent with a continued descent toward Shapley. This realization was decisive. Norma is massive, but not massive enough to account for the full motion. The gravitational narrative extends farther. Norma is part of the slope, not the pit. Shapley creates a gravitational well of extraordinary depth. Shapley's immense mass creates a gravitational well so deep that it may be one of the deepest in the nearby universe. This well shapes the motion of galaxies like water flowing into a vast, unseen basin. This gravitational depth is evident in the peculiar velocities of galaxies near and beyond Hydra Centaurus. Their acceleration increases as they approach Shapley's region, matching precisely the expected pull of a structure with Shapley's colossal mass. Cosmological simulations only match reality when Shapley's mass is included. When scientists simulate the cosmic flows around the Milky Way without including Shapley, the models fail. The predicted velocities are too small. The flow is too shallow. The direction is slightly off. But once Shapley's mass is added, everything falls into place. Velocities align. Flow directions match. The gravitational basin looks exactly like the one we observe in the universe. Shapley is not optional in modeling cosmic motion, it is essential. Shapley's dark matter far exceeds that of all neighboring clusters combined. The visible galaxies in Shapley are only the surface expression of an immense dark matter concentration. In fact, the dark matter halo surrounding Shapley is believed to outweigh the combined halos of Hydra, Centaurus, Norma, Virgo, and several other nearby clusters. This vast reservoir of dark matter explains why Shapley dominates the gravitational landscape. It bends spacetime across huge distances, creating the deepest part of the basin that defines our region of the universe. Shapley pulls the entire Laniakea supercluster toward it. Our home supercluster, Laniakea, contains around 100,000 galaxies, including the Milky Way. And Shapley pulls all of them toward its deep gravitational well. This means that Laniakea itself is not gravitationally isolated. It is embedded in a larger gravitational context, descending slowly toward Shapley like a drifting continent floating toward a deeper ocean trench. The entire structure of our cosmic neighborhood is shaped by Shapley's pull. It is one of the highest density regions within hundreds of megaparsecs. Within a radius of a few hundred megaparsecs, almost nothing rivals the density of the Shapley supercluster. Its mass concentration is exceptional. Clusters are tightly packed. Filaments are thick. Voids are minimized. This rare high-density environment makes Shapley a gravitational superpower. Its influence is detectable across enormous distances, shaping flows far outside its immediate boundaries. Galaxies beyond the Great Attractor drift even faster toward Shapley. As galaxies move past Hydra, Centaurus and Norma, their peculiar velocities often increase. This acceleration is a direct sign that they are descending into a deeper gravitational well. The farther they go, the stronger Shapley's influence becomes. Galaxies in its direction show systematically higher drift speeds, the unmistakable fingerprint of a massively dense region. This confirms that Shapley is the true gravitational peak of the region. Because galaxies accelerate as they approach Shapley, astronomers concluded that Shapley, not the Great Attractor, is the deepest, most influential mass concentration in our cosmic neighborhood. The Great Attractor shapes the early slope, but Shapley shapes the final descent. It is not a hilltop but a mountaintop of gravity, the summit toward which the entire landscape leans. Filaments connect the Great Attractor to Shapley and funnel matter into it. Cosmic filaments of dark matter bridge the gap between Hydra, Centaurus and Shapley. These filaments act as gravitational highways, channeling galaxies, gas, and dark matter from the Great Attractor region towards Shapley's deeper basin. This interconnected filamentary network explains why galaxy flows move seamlessly from one region to the other. The universe's hidden infrastructure ties them together in a single gravitational system. Shapley is the center of a massive gravitational continent. If the cosmic web were compared to an archipelago of continents, Shapley would be one of the largest land masses, an enormous gravitational continent composed of clusters, filaments, and dark matter planes. Its gravitational influence sweeps across vast swaths of the universe, shaping motions far beyond its own borders. It stands as the dominant feature in the local cosmic geography. It may be one of the largest superstructures in the nearby universe. Shapley's scale is so immense that some astronomers propose it as one of the largest coherent structures within several hundred million light-years. It dwarfs typical superclusters both in mass and extent. While the universe contains even larger giants, such as the Hercules, Corona Borealis Great Wall, Shapley is unique in its proximity and influence on our local cosmic flows. All of Laniakea may be a gentle slope leading toward Shapley. When scientists mapped the flow lines of galaxies in Laniakea, many of those lines pointed subtly toward Shapley. This suggests that the entire structure of Laniakea may be angled along a gentle gravitational slope descending toward Shapley's basin. In this perspective, Laniakea is not an isolated supercluster but one part of a much larger gravitational descent shaped by Shapley's distant mass. Shapley reveals the true nature of the Great Attractor, only a part of the slope. Once Shapley's mass was discovered and mapped, the Great Attractor's true nature became clear. It is not the ultimate cause of the cosmic flow, but merely the first step down a much longer gravitational incline. The Great Attractor is a doorway. Shapley is the destination. Understanding Shapley completes the cosmic picture, revealing the flows, slopes, and dark matter architecture that shape our galaxy's quiet drift through space. Laniakea includes the Milky Way, Virgo, Hydra, Centaurus, and the Great Attractor. Laniakea is the vast supercluster that encompasses many of the structures we call home. It includes the Milky Way, the Virgo cluster, the Hydra cluster, the Centaurus cluster, and even the broad gravitational region known as the Great Attractor. All of these systems are not isolated, but part of one immense, interconnected flow of galaxies drifting together through the cosmic dark. Laniakea stretches across hundreds of millions of light-years, binding these structures into a single gravitational landscape. It is the frame in which our galaxy's story unfolds, the larger environment shaping the paths of thousands of galaxies that share the same quiet drift. It is truly our parent supercluster. The concept of a parent supercluster may sound abstract, but Laniakea is exactly that. The gravitational domain within which the Milky Way resides. It is not simply a grouping of clusters, it is the structure that envelopes all of them, defining the cosmic basin we inhabit. When astronomers named it Laniakea, Hawaiian for immense heaven, they captured its essence. It is our universe-scale neighborhood, the grand structure holding together the flow that shapes our galaxy's movement through space. Laniakea is defined not by light, but by flow. Traditionally, superclusters were defined by the clustering of galaxies, by where light appeared densest. But Laniakea broke that rule. It is defined not by where galaxies are clustered, but by how galaxies move. Galaxies within Laniakea all drift toward a common region, the Great Attractor. Their motions reveal that they belong to a shared gravitational basin, even if they are separated by vast distances. Laniakea is the first supercluster ever defined entirely through cosmic flow, not brightness. About 100,000 galaxies belong to this shared flow. When astronomers traced the flow lines of galaxy motion, they discovered that roughly 100,000 galaxies, including our Milky Way, move as part of the same gravitational system. That means 100,000 galaxies are sliding together along the same broad slope of spacetime. Each one of these galaxies, from giant ellipticals to faint dwarfs, is a tiny light drifting along the invisible contours of Laniakea's gravitational valley. The gravitational center of Laniakea lies near the Great Attractor. The flow pattern that defines Laniakea converges near the Great Attractor. That region forms the gravitational center of the supercluster, not because it is the deepest point, but because it is the local minimum to which all surrounding galaxies drift before continuing onward. This does not mean everything falls into the Great Attractor, rather, it acts like the midpoint of a valley, the place where tributary flows merge before descending deeper toward Shapley. Laniakea spans about 500 million light-years. Laniakea is enormous, stretching roughly 500 million light-years across. This span is so vast that light takes half a billion years to travel from one side to the other. Inside this territory lie thousands of galaxy groups, hundreds of clusters, and countless filaments flowing through its gravitational terrain. Laniakea is one of the largest structures our galaxy participates in. It is not a bound structure, the universe still expands through it. Unlike galaxy clusters, superclusters like Laniakea are not gravitationally bound. The expansion of the universe dominates on such large scales. The galaxies inside Laniakea are not trapped in orbit. They drift because of shared gravity, but cosmic expansion continues to separate them gradually. Yet even amidst expansion, the local gravitational field is strong enough to shape their collective motion. Within its scale, gravity still outweighs local expansion. Expansion stretches space everywhere, but gravity holds influence on smaller scales. Within Laniakea, the gravitational pull of its clusters and filaments is stronger than the local expansion. This means galaxies inside Laniakea do not fly apart randomly. Their motions remain guided by the gravitational contours carved by enormous amounts of dark matter and clustered mass. Laniakea is like a cosmic drainage basin. The flow lines of galaxies within Laniakea resemble the flow of water across a drainage basin. Streams merge into rivers, which merge into channels, which ultimately flow toward a common low region in the terrain. Laniakea is exactly that, a gravitational watershed. Galaxies fall along gentle slopes, not rapidly but steadily, across hundreds of millions of years. All its galaxies drift in a shared direction. Despite the vast distances separating them, the galaxies of Laniakea drift toward the same general region. This coherence is one of the defining signatures of the supercluster. They are like countless fireflies moving in the same slow current, each following the curvature of spacetime sculpted by enormous masses around them. The Milky Way lies at the edge of Laniakea. Our galaxy is not at the center of anything. The Milky Way sits near the outer edge of Laniakea, like a small boat drifting along the rim of a massive cosmic river. We are not centrally placed, we are peripheral travelers, carried gently along the flow shaped by structures far larger than us. We are not in the middle, just one point along the flow. Because Laniakea is shaped by gravitational currents, not by physical boundaries, there is no true center. The Milky Way is simply one location along the flow lines, a participant, not a focal point. This perspective shifts our cosmic self-image. We occupy no privileged position. We are one of many galaxies gliding quietly through the same gravitational system. The Virgo cluster is only a small part of Laniakea. The Virgo cluster is often thought of as our dominant neighbor, and within the local supercluster, it is. But in Laniakea, Virgo is just one modest component in a much larger environment. It contributes to the flow but does not define it. Virgo is one tributary stream feeding the larger gravitational basin. The flow of Laniakea passes through the Great Attractor and then toward Shapley. Flow lines within Laniakea do not terminate at the Great Attractor. They pass through that region and continue deeper, eventually pointing toward the massive Shapley Supercluster. This reveals the layered nature of gravitational influence. Laniakea defines the basin, the Great Attractor forms the midpoint, and Shapley sits at the deepest part of the slope. This creates a full 3D motion map of our cosmic region. By tracing the peculiar velocities of galaxies inside Laniakea, astronomers built a three-dimensional velocity field map. This map shows not just where galaxies are, but where they are going. The result is a dynamic, moving portrait of our cosmic neighborhood, an image of drifting galaxies flowing along invisible routes carved by gravity. Laniakea contains many filaments leading to different clusters. Inside Laniakea, dark matter filaments stretch in multiple directions, connecting its clusters like highways. These filaments funnel galaxies and gas into larger structures, and they serve as the channels along which gravity pulls material inward. Each filament is a subtle gravitational pathway, shaping the movement of entire galaxy groups. Surrounding voids strengthen the direction of flow. The regions around Laniakea contain vast cosmic voids, immense empty spaces with extremely low density. These voids push galaxies away due to their lack of gravitational pull, effectively channeling the flow toward denser regions. The emptiness surrounding Laniakea amplifies the direction of the drift, making its gravitational basin even more distinct. Laniakea shows that the universe is more organized than we imagined. The discovery of Laniakea revealed that the universe is not a random scattering of galaxies. It is deeply structured, with vast regions shaped by coherent flows and gravitational boundaries. Instead of isolated clusters, we now see a cosmic architecture, rivers of galaxies, basins, ridges, and valleys created by dark matter and mass distribution on unimaginable scales. Laniakea is the largest structure the Milky Way is part of. The Milky Way participates in many structures: its spiral arms, its dark matter halo, the local group, the local sheet. But Laniakea is the largest of them all. It is the full extent of the gravitational environment that shapes our journey through the universe. Beyond Laniakea, we enter the domain of even larger structures, but those are not gravitationally tied to us in the same coherent way. We are drifting slowly within this giant cosmic home. Right now, the Milky Way is gliding slowly, silently, through Laniakea's gravitational basin. Every star, every nebula, every planet and moon is being carried along this massive cosmic flow. We are passengers in a drifting supercluster, floating through a universe far larger and more interconnected than we can ever fully see. Laniakea is our home, not in the way Earth is our home, but in the way the deep ocean is home to the currents that carry a ship. We are part of something vast, gentle, and ancient. Cosmic gravity is not like gravity on Earth. On Earth, gravity feels like a force pulling everything downward toward a single center. It creates clear, fall lines, making objects accelerate directly toward the ground. But on cosmic scales, gravity behaves differently. There is no single center. No universal down. Instead, gravity stretches and curves space itself, shaping it into gentle slopes and vast basins that matter naturally. Moves along. In the universe, gravity doesn't act like a magnet dragging galaxies straight in. It sculpts the terrain of spacetime. Galaxies don't fall, they drift, sliding along the contours carved by enormous amounts of dark matter and clustered mass. The cosmic version of gravity is more like the quiet shaping of a landscape by ancient, slow-moving tectonic forces. Over billions of years. It creates valleys, ridges, and expansive basins where galaxies glide silently through the dark. It does not create falling points, but slopes. Unlike the sharp gravitational pull we feel near Earth, cosmic gravity spreads its influence over vast distances. Instead of creating a single point where everything falls inward, it forms gradual slopes, broad regions where galaxies slide along the shape of curved spacetime. These slopes can span tens or even hundreds of millions of light-years. They are so gentle that galaxy motion is almost imperceptible in a human lifetime. Yet so powerful that they guide the trajectories of entire superclusters. Each slope is the result of mass, visible and invisible, accumulated across enormous cosmic volumes. Where mass piles up, spacetime dips. Where mass is scarce, spacetime rises. Galaxies respond to these slopes as naturally as a leaf floating along a tilted surface. There is no sudden fall. Only calm, persistent drifting. The Great Attractor is one of these intermediate slopes. The region we call the Great Attractor is not a gravitational epicenter. It is an intermediate slope on a much larger gravitational descent. It marks the place where the Milky Way and neighboring galaxies begin to slide more noticeably along the terrain shaped by Hydra, Centaurus, Norma, and the dark matter tying them together. Like a gentle bend in a descending mountain road, the Great Attractor redirects the flow but does not end it. Galaxies do not pool there. They continue onward, carried by the larger gravitational landscape whose deepest point lies elsewhere. The Great Attractor is a clue in the map, not the final destination. It is the visible sign that gravity is sculpting the universe on scales far beyond our imagination. Shapley is the deeper slope of the landscape. If the Great Attractor is the midpoint of a descent, the Shapley Supercluster is the deeper valley below. Its colossal mass pulls far more strongly than the Great Attractor. Peculiar velocities increase as galaxies approach it, revealing that Shapley shapes the gravitational terrain across hundreds of millions of light-years. In this cosmic landscape, Shapley is the deep end of the valley, the gravitational basin where countless flows converge. Its mass curves spacetime with extraordinary depth, creating a gravitational feature that extends far beyond its luminous clusters. Galaxies flow toward Shapley not because it is nearby, but because it is overwhelmingly heavy. Laniakea is the entire gravitational valley. If Shapley is a deep point and the Great Attractor is a midpoint, Laniakea is the entire valley itself, the full gravitational basin where flows are unified. This enormous structure contains around 100,000 galaxies all following similar flow lines, all sliding through the same large-scale curvature of spacetime. Laniakea is not defined by boundaries carved by light. Its edges are defined by where flows change direction, where galaxies stop drifting toward the Great Attractor Shapley slope and begin drifting elsewhere. In this sense, Laniakea is a basin in the truest meaning of the word. A gravitational drainage area, a cosmic bowl guiding the motion of entire superclusters. Galaxies do not fall, they glide. If cosmic gravity were like Earth's gravity, galaxies would accelerate rapidly toward Shapley. But because gravitational slopes are shallow and spread across enormous distances, galaxies glide instead of fall. Their motion is slow, steady, peaceful. This gliding behavior is why peculiar velocities appear modest relative to the ocean of expansion around them. The galaxies are not in freefall, they are drifting naturally along the soft curves of spacetime. Shaped by dark matter. The flow resembles water sliding down a dark riverbed. Imagine watching water move along a wide, shallow river at night. The flow is slow but persistent. It shapes the landscape and responds to it. This is how galaxies move along the cosmic web. The gravitational valley carved by dark matter acts like a riverbed, and galaxy clusters drift through it like glowing droplets. They follow the invisible path laid out beneath them. The cosmic web is not a rigid structure, it is a dynamic system where the motion of mass reveals the shape of spacetime, much like ripples reveal the shape of a riverbed beneath the water. Voids are the highlands of the gravitational terrain. Cosmic voids, huge regions nearly empty of galaxies, are the high areas in the gravitational landscape. They contain so little mass that spacetime curves upward, forming gravitational plateaus that gently push galaxies away. Galaxies do not fall into voids. They avoid them naturally, flowing instead toward denser regions where spacetime dips. This contrast between voids and clusters forms the backbone of the cosmic web's shape, highlands of emptiness and valleys of mass. Filaments are the valleys between voids. Filaments of dark matter and galaxies stretch across the universe like long, winding valleys. These filaments connect clusters, guiding galaxies along defined routes the way river. Valleys guide streams. Galaxies within filaments move coherently, following the gravitational descent along the filament's axis. These filaments are the structural bones of the cosmic web. And they are the pathways through which matter flows from high-density regions to deeper basins like Shapley. The Milky Way is sliding along one such gravitational roller coaster. Our galaxy is not stationary, it is gliding down one of these dark matter filaments, much like a roller coaster car slowly descending along a track. The path takes us through the local group, into the local sheet, past the Great Attractor region, and eventually toward Shapley. We are part of a vast, silent ride stretching across hundreds of millions of light-years. Every star you see in the night sky is moving with you, sharing that same gentle cosmic drift. Gravity shapes the flow, but expansion continues to stretch space. Two grand forces interact across the cosmos, gravity and expansion. Gravity sculpts the local terrain, creating slopes and basins. Expansion pulls everything apart globally. These forces coexist, shaping galaxy motion in complementary ways. Expansion determines the broad-scale separation of galaxies, but gravity determines the local flows within superclusters. It is like a river flowing across a drifting continent. The continent moves, but the water still finds its own path downward. This balance prevents galaxies from colliding on large scales. Because gravity creates slopes rather than violent drops, and expansion continues to widen distances. Galaxies rarely collide outside of bound structures. The flows are slow enough, and the expansion strong enough, that large-scale collisions are extremely rare. This balance is why galaxy clusters remain separate entities and why superclusters drift without merging into a single megastructure. Gravity guides, but expansion prevents collapse. These flows sculpt the shape of superclusters. The patterns of galaxy movement, how they glide along filaments, avoid voids, and slide into basins, ultimately shape the superclusters themselves. Superclusters are not random assemblies. They are products of flow, emerging where gravitational valleys shepherd galaxies together. Laniakea, Shapley, Perseus Pisces, each one is a gravitational sculpture created by billions of years of drifting matter. Flow boundaries define the borders between superclusters. Just as watersheds define the boundaries between river systems on Earth, flow lines define the borders of superclusters. Where galaxies stop drifting toward one basin and begin drifting toward another, the supercluster boundary is drawn. This method revealed the true extent of Laniakea and showed how it transitions into neighboring gravitational domains. Superclusters are not islands, they are drainage systems separated by invisible ridges. This is how the universe organizes itself over time. The cosmic web did not arise from randomness. It emerged from the interplay between dark matter, gravity, and expansion. Over billions of years, matter moved along gravitational slopes, flowing into basins, avoiding voids, settling into filaments. The result is an organized universe, a universe with a structure shaped by the soft but persistent hand of gravity. The flows are its brushstrokes. The basins are its canvas. Gravitational basins are the key to understanding the Great Attractor. The Great Attractor is not a point. It is a slope, a depression within a larger gravitational basin. Understanding it requires seeing gravity as terrain, not as a single pull. Only with this terrain-based view did astronomers realize that the Great Attractor is part of a larger descent leading toward Shapley. It is a curvature in the valley, not the valley's deepest point. Gravity on these scales is the primary architect of cosmic shape. On small scales, stars shape galaxies. But on large scales, gravity shaped by dark matter determines the architecture of the universe. It decides where filaments form, where clusters gather, where voids expand. Gravity becomes a vast, silent sculptor, working slowly over cosmic time to create the patterns we observe in the night sky. Without dark matter, there would be no gravitational valleys. Dark matter provides the mass necessary to carve deep gravitational basins. Without it, the universe would be too smooth. There would be no filaments, no clusters, no superclusters, only a weak, diffuse scattering of stars with little structure. Dark matter is the invisible clay from which gravity molds the cosmic terrain. Without it, the Great Attractor and Shapley would not exist. Without these valleys, there would be no bulk flow. Bulk flow, the coherent drift of galaxies across space, depends entirely on the presence of gravitational slopes. Without deep basins created by dark matter, galaxies would drift only with expansion, not sideways or inward. The entire story of the Great Attractor and Shapley is made possible by these valleys. They are the channels through which galaxies glide across the cosmic landscape. The universe is a giant relief map of invisible gravity. When you step back and look at the entire cosmic web, it resembles a vast relief map, a topographic landscape shaped by dark matter and gravity. Clusters are lowlands. Filaments are valleys. Voids are highlands. Light shows us only the surface, but gravity reveals the true shape underneath. The universe is a sculpture of invisible forces, and every galaxy is a traveler sliding quietly across its contours. The Milky Way has drifted along this flow for more than 10 billion years. Long before humans existed. Long before Earth was born, even long before the first spiral arms of the Milky Way were fully formed, our galaxy was already drifting along the great gravitational current of Laniakea. For more than 10 billion years, this silent motion has carried the Milky Way across cosmic space. The stars that light up our night sky were born into a galaxy already in motion, already gliding along a slope sculpted by dark matter and distant superclusters. This drift predates the Sun, predates the planets, predates nearly every structure we can see. The Milky Way has always been traveling. Moving not by force, but by the gentle pull of gravity spread across unimaginable distances. This flow began before the Milky Way was fully formed. The drift we experience today is not something that started after the Milky Way assembled. It began before the galaxy itself existed. The dark matter cloud that would one day become the Milky Way was already sliding through the gravitational terrain of the early universe. As the universe evolved, this cloud gathered gas, formed stars, and built the spiral disk we now call home, all while drifting. The motion is older than our galaxy. Older than most of its stars, woven into its very birth. The Milky Way's dark matter halo drifted long before the stars were born. Our galaxy is wrapped in a giant halo of dark matter, extending far beyond the spiral arms. This halo formed early in cosmic history, collapsing from the primordial density fluctuations that seeded the cosmic web. And from the moment it formed, it began drifting along the gravitational slope of Laniakea. The Milky Way's stars, gas clouds, and nebulae were added later, layering themselves inside an already moving dark matter structure. We live inside a galaxy that was already on its way somewhere long before we were part of it. This motion will continue far into the distant future. There is nothing temporary about the Milky Way's drift. It will continue for billions, trillions, even quadrillions of years, as long as gravity shapes spacetime and the universe continues to evolve. There is no stopping point, no final destination in the human sense. The Milky Way will keep gliding, slowly shifting across the cosmic web, long after the sun has burned out and long after the stars we know today have faded into darkness. This motion is as permanent as the universe itself. The Milky Way-Andromeda merger will happen within this flow. In about 4 billion years, the Milky Way and the Andromeda galaxy will merge. But this merger will not disrupt the larger cosmic flow. Both galaxies are traveling along the same gravitational current, drifting together toward Shapley. When they merge, the resulting elliptical galaxy, sometimes called Milkomeda, will continue its journey along the same path. On cosmic scales, the merger is merely a small ripple in a long river. The flow does not change because of the merger, it operates beyond the scale of clusters. The gravitational flow that guides the Milky Way and Andromeda is far larger than either galaxy. It is shaped by superclusters, by vast dark matter filaments, by structures hundreds of millions of light-years wide. A galaxy merger cannot alter this flow. It is like two leaves drifting into one another on a river, they may collide, swirl, and join, but the river continues carrying them downstream along the same path. The flow is simply too large, too ancient, too powerful to be changed by anything happening within a single galaxy. Laniakea remains the gravitational environment of our journey. No matter how the Milky Way evolves, Laniakea will remain its gravitational home. The entire supercluster is shaped by the flow of galaxies along the Great Attractor, Shapley Slope. This vast gravitational basin defines the motion of tens of thousands of galaxies, including ours. We are not merely living inside the Milky Way, we are living inside Laniakea, drifting across a landscape so large that even light needs 500 million years to cross it. The Milky Way will continue sliding down the gravitational slope toward Shapley. Shapley's gravitational well is the deepest influence within the region. The Milky Way's trajectory, and the trajectory of the entire Laniakea basin, bends subtly toward it. Over billions of years, our galaxy will drift ever closer toward that massive gravitational domain. But this approach is gentle, slow, and spread across cosmic timescales. It is not a fall. It is a glide, a gradual journey through a gravitational landscape shaped by unseen mass. Expansion ensures that distances remain safe and vast. Despite our drift toward Shapley, the expansion of the universe ensures that galaxies do not collapse endlessly into one another. Expansion stretches space itself, widening the gaps between superclusters even as local flows guide galaxies along gravitational slopes. This balance between expansion and gravity guarantees that the cosmic drift remains peaceful. There is no danger of the Milky Way crashing into Shapley's core. The universe expands too quickly at these scales for such collisions to occur. This drift has no impact on life on Earth. The Milky Way's motion is enormous in speed but subtle in effect. Nothing about this drift affects our solar system, our planet, or life on Earth. We don't feel it. We don't see it. It does not alter tides, climates, or orbits. It is the background motion, the quiet stage upon which the drama of life unfolds. Earth's history, evolution, and civilizations have all unfolded while our galaxy glided silently across the universe, completely unnoticed. It is simply the larger context of our galactic journey. Every planet, every star, every molecular cloud is moving with the Milky Way. This drift is the setting of our existence, a motion so slow, relative to human experience that it becomes invisible. Just as continents drift across Earth over millions of years without affecting daily life, our galaxy drifts across spacetime without disturbing the worlds inside it. It is the background, the quiet context of our cosmic story. A speed of 600 km per second sounds fast but is gentle on cosmic scales. To a human, 600 km per second is unimaginably fast, enough to circle Earth in less than a minute. But in the vastness of space, where distances are measured in millions of light-years, this speed is soft, calm, almost delicate. It is not a race. It is a glide. A peaceful movement guided by gravity, too slow to see, too vast to feel, but always present. This drift is one of the universe's quietest expressions of order. Despite the vastness, the darkness, and the apparent randomness of cosmic structures, the flow of galaxies reveals something beautiful, order within chaos. Galaxies are not scattered aimlessly. They follow subtle trails shaped by the gravitational terrain. The Milky Way's drift is part of that order, a sign that the universe is not silent but coordinated, not chaotic but structured. The Great Attractor teaches us that the most powerful influences are often invisible. The Great Attractor has almost no luminous signature. It is not bright. It is not obvious. And yet, Its gravitational influence shapes the motion of entire superclusters. It reminds us that not all forces announce themselves with light. Some of the most profound influences, in the cosmos and in life, are the ones we cannot see directly, only through their effects. The universe is not static, it is a slow, ongoing dance. Every galaxy is moving. Every filament is shifting. Every cluster is gliding across the cosmic web. The universe is not fixed. It is a dance, slow, vast, graceful. The Milky Way is one dancer among many, tracing a path through the dark, ancient choreography of gravity and expansion. We drift in this cosmic dance without ever feeling it. The floor beneath us, space-time itself, is moving. But because everything around us moves together, we sense nothing. Our motion is perfectly smooth, perfectly shared, perfectly silent. It is like floating on a raft in a vast ocean at night. You feel still, even as the entire sea carries you forward. Every star around us moves along the same flow. The entire galaxy, its 400 billion stars, is carried along the same current. Every constellation, every nebula, every glowing swirl in the Milky Way shares this drift. We are part of a collective motion, a vast caravan of starlight moving together toward deeper gravitational valleys. All of Laniakea is a slow-drifting ocean. Laniakea is not static. It is a giant, drifting ocean of galaxies. Clusters swirl like eddies. Filaments stretch like deep currents. Voids rise like highlands. And everything, absolutely everything, is moving. Not chaotically, but rhythmically. The flow reveals the hidden structure of the universe the way tides reveal the shape of the ocean floor. The Milky Way is only a small boat on this vast cosmic current. Our galaxy may contain billions of stars, but within Laniakea it is tiny, a small vessel carried by a gravitational sea. It does not steer its path. It drifts, gently and inevitably, along the slope carved by mass far beyond itself. We live on a little ship sailing through a gravity-shaped ocean. And you, as you drift into sleep, are drifting with the entire galaxy. As you close your eyes and let your breath soften, remember that you are moving. Right now. Always. You are drifting with Earth, drifting with the Sun, drifting with the Milky Way, drifting with all of Laniakea. Carried on a silent river of gravity stretching across the universe. You are part of this cosmic motion, part of this ancient journey, part of this grand, peaceful drift through the stars. And as you fall asleep, you drift a little deeper. A little quieter. Along with the galaxy that carries you gently through the night.